You are listening to Architecting the Future, a practical guide to microservices design, implementation, and patterns. Like and subscribe to keep up to date on our latest audiobooks. Architecting the Future, a practical guide to microservices design, implementation, and patterns. Chapter 1, The Software Evolution, Why Microservices? Software development is a constantly evolving landscape. What was once considered a cutting-edge architectural approach can, within a few years, become a source of technical debt and operational headaches. Technologies emerge, business demands shift, and user expectations soar. In this whirlwind of change, organizations are endlessly seeking the optimal way to build and manage applications that are not only powerful and reliable, but also adaptable and scalable. For many, that search has led to an architectural style known as microservices. But before we dive into what microservices are and how to design and implement them, it's crucial to understand why they came to be. Their rise is not just a technological fad. It's a direct response to the inherent limitations of their predecessors, particularly the monolithic application. The monolithic predicament. For a long time, the dominant way to build enterprise-scale software was as a monolith. Imagine a traditional brick-and-mortar library. It's a single, massive building housing everything: the book stacks, the librarian's desk, the checkout system, the research computers, and the coffee shop. All these components are bundled together, sharing the same foundation and infrastructure. In software terms, a monolithic application is a single, unified codebase where all functionalities, user interfaces, business logic, data access layers, and external integrations are packaged and deployed as one large, indivisible unit. Early in an application's lifecycle, this approach offers several advantages. Simplicity of development. For small teams and straightforward applications, development within a single codebase can be quick and hassle-free. Everything is in one place, making initial navigation and understanding relatively easy. Easier deployment. There's only one artifact to deploy. Copying a single file or executable to a server, or a few servers for redundancy, is less complex than orchestrating dozens or hundreds of individual components. Simplified debugging. In a single process, tracing requests and understanding how different parts of the application interact is more straightforward. You don't have to worry about network latency or interprocess communication issues. However, as applications grow in size, complexity, and user base, these initial advantages steadily transform into significant drawbacks. The once manageable library building starts to buckle under the strain. Scalability bottlenecks. What if your library's checkout desk is always swamped, but the research section is often empty? In a monolithic system, you can only scale the entire building. If one component of your application, like the order processing module, faces high demand, you have to scale the entire application, including parts that don't need scaling, leading to inefficient resource utilization. Sluggish development cycles. As more developers join and the codebase balloons, making changes becomes a daunting task. A developer working on a new feature in the reports section might inadvertently introduce a bug in the user authentication module because all code lives together. This leads to longer testing cycles and a fear of deploying anything for fear of breaking the whole system. The term fear of deployment becomes common. Technology lock-in. Once you choose a particular programming language, framework, or database for your monolith, you're largely stuck with it. Replacing a critical component might mean rewriting the entire application. The library only has one type of wall, and changing it means rebuilding the whole structure. Tight coupling and dependencies. Every part of the monolith is deeply interconnected. A small change in one module often necessitates exhaustive testing of seemingly unrelated parts. This tight coupling means bugs can easily cascade and innovation is stifled. Increased cognitive load. For new team members, understanding a massive codebase can take months. Even experienced developers struggle to hold the entire system's logic in their minds. Single point of failure. If one small part of the monolith fails, it can bring down the entire application. A bug in the recommendations engine might crash the entire e-commerce site, even if the checkout system itself is perfectly fine. The solution to these growing pains eventually centered on the idea of breaking down these immense, tightly bound systems into smaller, more manageable pieces. The emergence of microservices. The concept of breaking down large systems isn't entirely new. Service-oriented architecture, SOA, which gained prominence in the early 2000s, advocated for building applications from loosely coupled, reusable services. Microservices architecture, in many ways, is a more refined, opinionated, and cloud-native evolution of these principles. The need for microservices crystallized around several key shifts in the software industry. The rise of cloud computing. Cloud platforms offered unprecedented flexibility for deploying and scaling individual components. Why deploy one giant application to a virtual machine when you could deploy many smaller, specialized components and scale each independently on demand? The DevOps movement. The imperative to achieve faster, more reliable software delivery cycles pushed organizations to automate everything, from code commit to production deployment. Monoliths, with their lengthy build and test times, were a natural bottleneck. Agile methodologies. Agile development emphasizes small, self-organizing teams rapidly delivering value. A monolithic architecture often clashed with this, as large teams found themselves tripping over each other in a shared codebase. One of the most widely cited pioneers in microservices adoption was Netflix. As their streaming platform grew from a DVD-by-mail service to a global media giant, their monolithic application simply couldn't keep up with the demand or the pace of innovation. A single database corruption once brought down their entire service for 3 days. This pivotal incident drove their decision to migrate to a highly distributed, cloud-based microservices architecture. Today, Netflix is powered by thousands of independent services, each handling a specific function like user authentication, video recommendations, or content streaming. This allowed them to achieve unprecedented scalability, resilience, and deployment velocity. This shift wasn't just about technology. It was about enabling organizations to respond more quickly to market demands, improve system resilience, and empower their development teams. A company's tipping point, the story of global retail. Consider the fictional company, Global Retail. 5 years ago, they launched their e-commerce platform as a single, powerful website. It handled everything: product catalogs, customer accounts, shopping carts, order processing, and payment integration. It was efficient, tightly knit, and easy for their small team of 10 developers to manage. Fast forward to today. Global Retail has expanded internationally, acquired smaller businesses, and now offers delivery services. Their single application, once a source of pride, has become a liability. "We can't even touch the checkout code without holding our breath," explained Sarah, the lead developer, during a tense strategy meeting. Last month, a small bug fix in the returns section, a completely separate part of the business logic, mind you, introduced a caching error that prevented payments in Europe for 3 hours. It took us half a day just to figure out what happened in that giant codebase. Mark, the head of operations, chimed in, and deployments are a nightmare. "We used to deploy weekly, now it's once a month if we're lucky. Each deploy means taking the entire site offline for maintenance, and the risk of something breaking is so high that we schedule them for 3 a.m. on Sundays. Our competitors are pushing new features daily." The marketing team was frustrated too. "We want to A/B test a new product recommendation engine, but integrating it into the core system would take months of development and risk destabilizing everything. We're losing market share because we can't innovate quickly." The technical debt was mounting. Onboarding a new developer now took 3 months just to understand the sprawling architecture. Any attempt to upgrade a core library or database version was met with dread, as the intertwined dependencies meant a ripple effect of unforeseen consequences. It became clear. Global Retail had outgrown its single, comfortable building. They needed a new approach, one that would allow them to scale individual departments, introduce new services without disrupting existing ones, and empower their growing teams to innovate at speed. Their tipping point had arrived, driving them towards a more distributed, flexible way of building software microservices. What this book will cover. The journey to microservices, while immensely rewarding, is not without its challenges. It introduces new complexities in communication, data management, testing, and operations. This book is designed to be your practical guide through this journey. We will start by deeply unpacking what microservices truly are, moving beyond the buzzwords to understand their core characteristics and the philosophy behind them. We will then delve into the fundamental principles of designing microservices, helping you define appropriate boundaries and choose the right communication patterns. We'll explore the intricate world of distributed data management, and then equip you with the knowledge to deploy, monitor, and secure these distributed systems effectively. Finally, we will dive into a rich catalog of microservices design patterns, discuss advanced concepts like service mesh and serverless, and provide strategies for migrating from existing monolithic applications, always keeping an eye on the crucial organizational changes required for success. Our goal is to provide a comprehensive, factually accurate, and engaging resource that empowers you to confidently design, implement, and operate microservices architectures. Whether you are a seasoned architect, a curious developer, or a strategic business leader, by the end of this book, you will not only understand the why and what of microservices, but also the practical how to architect the future of your software. Chapter 2: Unpacking Microservices. Beyond the buzzword. In the previous chapter, we explored the forces that led to the emergence of microservices architecture, the limitations of monolithic systems, the rise of cloud computing, and the demands of agile development and DevOps. Now, it's time to peel back the layers and understand what microservices truly are. It's more than just breaking a big application into smaller pieces. It's a distinct architectural style with specific characteristics, principles, and even a unique philosophy. Defining microservices: small, focused, independent. At its core, a microservice is a small, autonomous service designed to perform a single, well-defined business function. It runs in its own process and communicates with other services, typically over a network, using lightweight mechanisms like HTTP APIs or message queues. Think of building with Lego blocks versus molding clay. A monolith is like a sculpture molded from clay. Everything is connected, and changing one part often requires reshaping the whole. Microservices are like a structure built from Lego blocks. Each block is distinct, self-contained, and can be swapped out or reconfigured without affecting the others, provided the connection points remain consistent. The most widely accepted definition, provided by notable figures like Martin Fowler and James Lewis, highlights these key aspects. Small and focused. Each service should be small enough to be understood by a single developer or a small team. Its scope is limited to a specific business capability, like order management or user authentication, rather than an entire application. Independent. Services are independently deployable, scalable, and testable. A change in one service doesn't require redeploying or even restarting other services. Loosely coupled. Services have minimal dependencies on each other. They communicate through well-defined APIs or messages, and internal implementation details of one service are hidden from others. Highly cohesive. The code and data within a service are tightly related and work together to fulfill its specific business function. Characteristics of a microservice architecture. Beyond the basic definition, a microservices architecture embodies several distinctive characteristics that set it apart. 1. Componentization via services. In a monolithic application, different logical components, e.g., user interface, business logic, data access, are typically organized as libraries or modules within a single process. With microservices, these components are broken out into separate services. An order service might contain its own business logic for order processing, its own database for storing orders, and its own API for other services to interact with it. This move from in-process modules to distinct, network-addressable services is fundamental. 2. Organized around business capabilities. Unlike traditional architectural approaches that often layer applications horizontally, e.g., UI layer, business logic layer, data layer, microservices are typically organized vertically around specific business capabilities. This means a single service owns all the necessary components, user interface snippets, backend logic, and its own database, required to fulfill a particular business function. For instance, instead of a generic user management layer, you might have a customer service that manages customer profiles, orders, and preferences. This fosters strong ownership and alignment with real-world business domains. 3. Products, not projects. Traditionally, software development often operates on a project basis. A team builds a piece of software, launches it, and then moves on to the next project. With microservices, the mindset shifts. Each service is treated as a long-lived product that evolves over time. The team responsible for a service owns it for its entire life cycle, from development to deployment, operations, and eventual retirement. This "you build it, you run it" philosophy fosters greater accountability, quality, and domain expertise. 4. Smart endpoints and dumb pipes. This characteristic highlights the communication philosophy in microservices. Services are designed to be quite smart about their own logic and processing, but they communicate with each other through simple, dumb mechanisms. Smart endpoints. Each microservice is intelligent. It knows how to fulfill its responsibilities, manage its own data, and process requests. It contains complex business logic. Dumb pipes. The communication channels between services are kept as simple as possible. This typically means using lightweight, protocol-agnostic mechanisms like REST-TFL HTTP or simple message queues like Kafka or RabbitMQ. There's no central, complex enterprise service bus, ESB, that orchestrates complex logic or converts messages. Services communicate directly or via simple message brokers, passing data from one point to another without adding much intelligence to the pipe itself. 5. Decentralized governance and technology diversity. In a monolithic architecture, the choice of technology stack is usually made once and applied universally. All developers must use the same programming language, framework, and database. Microservices, however, embrace decentralized governance. Each service, or the team owning it, is free to choose the best technology for its specific purpose. If the recommendation service needs to process vast amounts of real-time data, it might use a NoSQL database like Cassandra and be written in Scala. Meanwhile, the payment service, which requires strong transactional consistency, might use a relational database and be written in Java. This polyglot persistence and programming allows developers to leverage the strengths of different technologies, fostering innovation and avoiding the lowest common denominator approach. 6. Decentralized data management. A critical characteristic, and often a challenging one, is that each microservice owns its own data store. This means an order service has its own database that other services do not directly access. If the customer service needs information about orders, it must request it via the order services API, not by querying the order services database directly. This concept, known as database per service, reinforces autonomy and loose coupling, preventing tangled database dependencies common in monoliths. It introduces challenges around data consistency, which we will address in a later chapter. 7. Infrastructure automation. Developing, deploying, and managing potentially hundreds or thousands of services manually is impossible. Microservices architectures rely heavily on infrastructure automation, particularly continuous integration, CI, and continuous delivery, CD. Tools for automated building, testing, packaging into containers like Docker images, and orchestrating deployments using platforms like Kubernetes are indispensable. This automation ensures that services can be deployed quickly and reliably, often multiple times a day, without human intervention. 8. Resilience and failure isolation. Because microservices are distributed systems, they must be designed to anticipate and gracefully handle failures. If one service fails, it should not bring down the entire application. Techniques like circuit breakers, bulkheads, and retries are employed to isolate failures and ensure that the system as a whole remains available, albeit potentially with degraded functionality. This focus on designing for failure is paramount. The microservices landscape. To bring these characteristics to life, it helps to visualize the typical components within a microservices ecosystem. Individual microservices. These are the core business logic units, each with its own specific function, e.g., product catalog, user profile, shipping. APIs. Each microservice exposes a well-defined application programming interface, API for communication. This is often a REST-full HTTP API. API gateway. For external clients, web browsers, mobile apps, there's typically a single entry point known as an API gateway. It routes requests to the appropriate microservices, handles authentication authorization, and can perform request aggregation. Message brokers queues. For asynchronous communication, services often use message brokers, like Apache Kafka or RabbitMQ. Services publish events or messages, and other services subscribe to consume them, allowing for highly decoupled interactions. Service discovery. In a dynamic environment where services are constantly scaled up, down, or moved, services need a way to find each other. Service discovery mechanisms, like Eureka, Consul, or Kubernetes DNS, allow services to register themselves and locate others. Containers and orchestration. Microservices are often packaged into lightweight, portable units called containers, e.g. Docker. These containers are then managed and orchestrated at scale by platforms like Kubernetes, which automate deployment, scaling, healing, and networking. Observability tools. Given the distributed nature, tools for centralized logging, monitoring, and distributed tracing are critical to understand system behavior, diagnose issues, and ensure performance. Common misconceptions. Despite their popularity, microservices are often misunderstood. Just breaking up a monolith. While it involves decomposition, microservices are not simply about cutting a monolith into arbitrary pieces. It requires careful thought about business boundaries and communication. A distributed monolith that struggles with tight coupling and shared databases despite being physically separated is a common anti-pattern. A silver bullet. Microservices aren't a panacea for all software challenges. They introduce their own set of complexities, including increased operational overhead, distributed debugging challenges, and the need for significant cultural shifts. For small, simple applications, a well-designed monolith might still be the more appropriate choice. We will explore this trade-off in the next chapter. Micro implies tiny. The micro in microservices refers more to their bounded context and functional scope, not necessarily lines of code. A service could be hundreds or even thousands of lines of code, as long as it adheres to the other principles. Key takeaway: more than just technology. Ultimately, microservices embody a significant architectural paradigm shift, but they also represent a profound cultural and organizational change. They demand autonomous, cross-functional teams, a strong DevOps culture, and a commitment to automation. They push organizations to align their technical capabilities more closely with their business structure. As codified by Conway's Law, organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. This architectural style enables agility, resilience, and independent evolution, allowing organizations to adapt quickly to ever-changing market demands. However, successfully adopting microservices requires more than just understanding the technology. It demands a holistic rethinking of how software is built, deployed, and operated, and how teams are structured and empowered. In the following chapters, we will equip you with the knowledge to make informed decisions about this powerful but complex architectural style. Chapter 3: Monolith to Microservices, a strategic shift. In the previous chapters, we've established why microservices emerged and what defines them. Now comes the critical question for any organization. When should you consider making the strategic shift from a monolithic architecture to microservices? And just as importantly, when should you not? This decision is not merely technical. It has profound implications for your team, your processes, and your bottom line. The decision-making framework. Migrating to microservices is a significant undertaking, requiring investment and commitment. It's crucial to make this decision based on a clear understanding of your specific needs, resources, and long-term goals. There's no one-size-fits-all answer, but we can outline a framework to guide your strategic shift. Factors favoring microservices. You should seriously consider microservices if your situation aligns with several of these points. Large and complex systems. Your application's codebase is growing beyond the manageable limits of a single team. You've experienced fear of deployment or fear of change due to the interconnectedness of your existing monolith. Need for high scalability and availability. Certain parts of your application experience fluctuating or extremely high load, while others do not. You need to independently scale specific components to handle bursts of traffic without over-provisioning resources for the entire system. You also require high availability, where the failure of one component does not bring down the entire system. Diverse technology needs. Different parts of your business domain or specific functionalities require different technology stacks, programming languages, or database types to achieve optimal performance or development efficiency. You want to avoid technological lock-in. Large and distributed teams. You have multiple, independent teams working on different features or parts of the application. A monolithic codebase often leads to coordination overhead, merge conflicts, and slow development cycles in such environments. Microservices align well with autonomous, cross-functional teams. Rapid release cycles and continuous delivery. You need to deploy new features, bug fixes, or updates frequently, ideally multiple times a day or week, with minimal downtime. The lengthy build, test, and deployment cycles of a monolith become a significant bottleneck. Long-term evolution and innovation. You envision your application evolving significantly over many years, adapting to new business requirements and technological advancements. Microservices promote maintainability and allow for easier introduction of new technologies. Factors favoring monoliths, or sticking with one. Conversely, adopting microservices might be an over-engineering for your current context if small teams and simple applications. You have a small development team, e.g., 2 to 5 developers, and your application is relatively straightforward, with a limited scope. The overhead of managing a distributed system would outweigh the benefits. Limited budget and resources. Establishing and maintaining a microservices architecture requires significant investment in infrastructure, automation tools, monitoring systems, and skilled personnel. If your budget is constrained, starting with a monolith can be more cost-effective. Early-stage startups. When you're building a new product and proving out a business model, speed is paramount. A monolith allows for faster initial development and iteration, letting you reach product-market fit more quickly. Premature optimization or over-architecting can lead to unnecessary delays. No clear domain boundaries. If your application's functionalities are so tightly intertwined that independent components are difficult to define, perhaps due to an undifferentiated business domain, forcing a microservices architecture might lead to a distributed monolith, which has all the complexity but none of the benefits. The trade-offs, a balanced perspective. Making a strategic shift to microservices means accepting a different set of trade-offs. It's not about being better or worse than a monolith, but about being different and more suitable for specific contexts. Benefits of microservices. Faster, independent deployment. Each service can be deployed independently. This means faster release cycles and the ability to release critical updates without impacting other parts of the system. Improved scalability. You can scale individual services based on demand, optimizing resource utilization. If your user authentication service is under heavy load, you can scale only that service, not the entire application. Technological flexibility. Teams can choose the best language, framework, and database for each service, avoiding technology lock-in and allowing for innovation. Better fault isolation. The failure of one service is localized and, with proper design, shouldn't cascade and bring down the entire application. Easier maintenance and understanding. Smaller code bases for individual services are easier for developers to comprehend, maintain, and refactor. Stronger team ownership. Autonomous teams owning specific services end-to-end fosters accountability and expertise, aligning well with DevOps principles. Challenges of microservices. Increased operational complexity. Deploying, monitoring, and managing many separate services is significantly more complex than managing a single monolith. You need robust CI/CD pipelines, centralized logging, distributed tracing, and skilled operations teams. Distributed data management challenges. Maintaining data consistency across multiple independent databases is difficult. Concepts like eventual consistency and saga patterns become crucial but add complexity. Inter-service communication overhead. Network latency, reliability, and managing communication protocols between numerous services introduce new failure modes and debugging complexities. Distributed debugging. Tracing a request that spans multiple services requires specialized tools and techniques, such as distributed tracing systems. Higher initial setup cost. The upfront investment in infrastructure, automation, and organizational restructuring can be substantial. Organizational changes. Successfully adopting microservices often requires restructuring teams, redefining roles, and fostering a strong DevOps culture. This change management can be the hardest part. Testing complexity. Testing an application composed of many interacting services is more challenging than testing a single unit. Strategies like consumer-driven contracts become essential. Cost-benefit analysis. Beyond just technical debt. When evaluating the shift, look beyond just technical considerations. Factor in the operational and organizational costs. Operational costs. Will your existing operations team be able to handle the increased complexity of a distributed system? Do you need to hire specialists or invest heavily in automation tools? Development costs. While development might speed up for individual services, the initial investment in setting up the microservices ecosystem can be high. Training costs. Do your developers and operations staff have the skills needed for designing, building, and running distributed systems? If not, significant training will be required. Opportunity cost. What are you not doing while you are investing in this architectural shift? Is the business value gain worth the diversion of resources? The Goldilocks zone. Finding the right service size. A common question when decomposing an application is, how big should a microservice be? There's no magic number of lines of code or developers. The Goldilocks zone for a microservice is just right. Not too big, a distributed monolith. If a service becomes too large, it inherits many of the same problems as a monolith, slow development, tight coupling internally. Not too small, too granular. Creating too many tiny services, each with trivial functionality, can lead to communication overhead, network calls between too many services, and management complexities that outweigh the benefits. This is often called nanoservices and should be avoided. Instead of size, focus on cohesion and business capability. A service should encapsulate a single, well-defined business capability and be highly cohesive internally. It should ideally be owned by a single, small, autonomous team. Avoiding the distributed monolith. One of the greatest dangers in microservices adoption is ending up with a distributed monolith. This anti-pattern occurs when you technically split your application into separate services, but they remain tightly coupled in practice, often due to shared databases. Multiple services directly accessing the same database creates a hidden dependency. Changes to the database schema by one service can inadvertently break others. Synchronous inter-service communication. Services that rely too heavily on synchronous calls to many other services create a fragile chain. If one service in the chain goes down, the entire user request might fail. Tight coupling through shared libraries or contracts. While component sharing can be good, oversharing of domain objects or internal implementation details between services can lead to an inability to deploy services independently. Lack of autonomy. Teams are not truly empowered to deploy or evolve their services independently, necessitating complex coordination before any change can be released. A distributed monolith gives you all the operational complexity of distributed systems without the benefits of independent deployability, scalability, or team autonomy. This is often a worse state than a traditional monolith. Case study insight: the Fast Flow Logistics saga. Fast Flow Logistics, a mid-sized shipping company, began its journey to microservices with enthusiasm, but without a deep appreciation for the underlying principles. Their legacy system, a monolithic application handling package tracking, delivery scheduling, and customer communication, was indeed cumbersome. Developers complained about 3-hour build times and often broke each other's features. Their initial strategy was to simply split the front end from the back end, and then further break down the back end into package service, customer service, and delivery service. However, they kept a single, large relational database. "We thought we were doing microservices," recounted Alex, a veteran developer at FastFlow. "The services were separate processes, each had its own deployable unit. But if I changed a column in the packages table, every single service that used that table, which was all of them, had to be updated and redeployed simultaneously. What was the point? We spent more time coordinating database schema changes than writing new features." Their customer service relied on the package service to get package status, and the delivery service relied on both. All communication was synchronous. A transient network glitch between any two services would routinely cause a cascade of failures, leading to widespread, service unavailable errors for customers. They had simply taken their monolith and distributed it, magnifying its inherent coupling problems. It took them 2 years of painful lessons, including several major outages, before they truly understood decentralized data management and embraced asynchronous communication patterns. They learned that microservices are not just about physical separation, but about achieving true logical and data autonomy. Conclusion: a calculated choice. The move to microservices is not a default recommendation for every software project. It's a strategic architectural choice, best suited for complex, evolving, and high-scale systems where agility, independent scalability, and organizational alignment are paramount. It's a significant investment that requires careful planning, a strong focus on automation, and an understanding of the cultural changes required. By understanding the true trade-offs and diligently working to avoid the pitfalls, organizations can leverage microservices to build resilient, adaptable, and highly performant applications that truly architect their future. Chapter 4: Core Principles of Microservices Design. Having understood the rationale behind microservices and the strategic decision-making process, we now arrive at the heart of the matter. How do we design individual microservices and the ecosystem they inhabit? This is where theoretical understanding translates into practical application. Poor design can render a microservices architecture more problematic than a monolith, leading to what many call a distributed hell. Conversely, well-designed microservices unlock immense agility, scalability, and resilience. This chapter lays out the foundational design principles that guide successful microservices adoption. These are not rigid rules, but rather guidelines and philosophies that, when embraced, lead to robust and maintainable distributed systems. 1. Single Responsibility Principle, SRP, applied to services. You might be familiar with the Single Responsibility Principle, SRP, from object-oriented programming, where a class should have only one reason to change. In microservices, SRP is elevated to the service level. A microservice should have one and only one reason to change. This means each service encapsulates a single, specific business capability. For example, in an e-commerce system, a product catalog service manages product information. Its reason to change is a change in how products are defined, searched, or displayed. An order service handles order creation, status updates, and fulfillment logic. Its reason to change is a change in the ordering process. A payment service processes transactions. Its reason to change is a change in payment methods or payment processing rules. If a service is responsible for too much, it becomes a miniature monolith, potentially introducing the same coupling and complexity issues that microservices aim to solve. Adhering to SRP keeps services small, manageable, and focused, making them easier to develop, test, and deploy independently. 2. Loose coupling and high cohesion. These two concepts are cornerstones of good software design, applicable at all levels, but particularly critical in distributed systems. Loose coupling. This refers to the degree to which components depend on each other. In a loosely coupled system, a change in one service has minimal or no impact on other services. Services interact through well-defined, stable interfaces, APIs, and don't make assumptions about each other's internal implementation details. Analogy: think of electrical plugs and sockets. Each appliance service has a standard plug API that fits into any standard socket. You can swap out a toaster for a coffee maker without needing to rewire your house. High cohesion. This refers to the degree to which elements within a module or service belong together. In a highly cohesive service, all its parts work collaboratively to achieve a single, well-defined purpose. The functions, data, and logic within a service are strongly related. Analogy: a highly cohesive service is like a specialized tool, e.g., a hammer. All its parts, head, handle, are designed to work together for one specific purpose, driving nails. A low cohesive service would be like a hammer, screwdriver, wrench, bottle opener, multi-tool. It tries to do too many things and does none of them particularly well. The goal is to design services that are highly cohesive internally and loosely coupled externally. This allows teams to develop and deploy services independently, reducing the ripple effect of changes across the entire system. 3. Bounded context. Introduction to DDD principles. The concept of bounded context comes from domain-driven design, DDD, a software development approach focused on tackling complex domains by connecting the implementation to an evolving model. It is perhaps the single most important principle for defining microservice boundaries. A bounded context is a logical boundary within which a specific domain model is defined and applicable. Terms and concepts within one bounded context might have different meanings or interpretations in another. Example: in an e-commerce domain, product could mean different things. In the catalog bounded context, a product might include attributes like name, description, image URLs, and categories. In the inventory bounded context, a product might focus on stock levels, warehouse locations, and availability dates. In the shipping bounded context, a product might be concerned with weight, dimensions, and shipping restrictions. Trying to create a single, unified product model across all these contexts leads to complexity, compromises, and a bloated domain model that satisfies no one. Instead, each bounded context has its own, simpler model for product that suits its specific needs. For microservices, the implication is clear. Each microservice should ideally correspond to a single bounded context. This provides a natural and robust way to draw service boundaries, ensuring that each service has a clear responsibility and its own internal model, reducing coupling and improving clarity. 4. Conway's Law. Conway's Law, articulated by Melvin Conway in 1968, states, "Any organization that designs a system, defined broadly, will produce a design whose structure is a copy of the organization's communication structure." In the context of microservices, this means that if your development teams are organized by technical layers, e.g., a UI team, a backend team, a database team, you are likely to build a monolithic application with distinct layers. Conversely, if you want a microservices architecture where each service is owned end-to-end, you should organize your teams around business capabilities. An order management team would own the order service from front-end to back-end, including its database. Embracing Conway's Law is crucial because it highlights that adopting microservices is as much an organizational change as it is a technical one. Restructuring teams to be cross-functional and autonomous, each owning a specific set of microservices aligned with a business capability, is fundamental to realizing the benefits of this architectural style. 5. Service autonomy. The concept of autonomy underpins many of the benefits of microservices. A microservice should be truly independent deployability. A service can be deployed, updated, or rolled back without affecting other services. This is perhaps the most significant operational advantage. Independent scalability. Each service can be scaled up or down based on its own specific load requirements, optimizing resource usage. Independent failure. If one service fails, it should not bring down the entire system. Other services should continue to function, perhaps with graceful degradation. Autonomous evolution. The team owning a service can make technology choices, iterate on its design, and release new versions without complex cross-team coordination, as long as it respects its public API contract. This autonomy is achieved by strictly enforcing loose coupling, avoiding shared databases, and promoting clear boundaries. 6. Resilience and failure tolerance. Microservices are distributed systems, and distributed systems fail. Network latency, service unavailability, and transient errors are facts of life. Therefore, a core design principle is designing for failure. Rather than hoping failures don't happen, anticipate them and build mechanisms to cope gracefully. Circuit breakers. Prevent an application from repeatedly trying to access a service that is down or experiencing problems, avoiding cascading failures. Timeouts and retries. Configure services to wait for a reasonable period for responses and to retry operations that are likely to succeed on a subsequent attempt. Bulkheads. Isolate unresponsive or failing services, preventing them from consuming all available resources, e.g., threads in a thread pool, thereby protecting healthy parts of the system. Graceful degradation. Design your application to provide reduced functionality or a simpler user experience when certain services are unavailable, instead of a complete outage. This principle shifts the mindset from if it fails, fix it, to when it fails, recover gracefully. 7. Observability. In a monolithic application, debugging might involve grepping through a single log file or attaching a debugger to a single process. In a microservices environment, a single user request might traverse dozens of services across multiple machines, making traditional debugging extremely challenging. Observability is the ability to understand the internal state of a system by examining its external outputs. For microservices, this means designing services to be transparent from the outset. Centralized logging. Aggregate logs from all services into a single, searchable repository. Monitoring and metrics. Collect and visualize key performance indicators, KPIs, and health metrics from each service. Distributed tracing. Track individual requests as they propagate through multiple services, providing a holistic view of their journey and identifying performance bottlenecks. Health checks. Expose endpoints that allow monitoring systems to check the operational status and readiness of a service. Without robust observability, operating a microservices architecture becomes a blind and frustrating endeavor. 8. Dry don't repeat yourself versus DUP, don't repeat production. The don't repeat yourself dry principle is fundamental in traditional software development, advocating for abstracting common code into reusable libraries. While still valuable, in a microservices context, its application needs careful consideration. Overzealous application of dry can lead to problematic shared libraries that introduce tight coupling between services, defeating the purpose of independent deployment. If a shared library changes, all services using it might need to be updated and redeployed simultaneously, essentially creating a distributed dependency. Instead, a subtle shift towards don't repeat production, DUP, or copy-paste with pride is often advocated. If a piece of common functionality, e.g., date formatting, currency conversion, is not central to business logic and is unlikely to change frequently or break other services if it does, it might be acceptable to duplicate a small amount of code across services rather than forcing a shared library. For truly cross-cutting concerns, like authentication, logging, or tracing, these are often handled by frameworks, sidecars, or an API gateway, rather than by tightly coupled shared libraries. The trade-off is between code reuse and service autonomy. Prioritize service autonomy where independent development and deployment are critical. Practical application. Decomposing an e-commerce domain. Let's imagine applying these principles to break down a monolithic e-commerce application. Starting point: a single code base handling everything from user accounts to payments. Applying principles. Bounded contexts plus SRP. Identify clear business capabilities: accounts, catalog, inventory, order, payment, shipping, recommendations. Each becomes a potential service, or groups of services if very complex. Loose coupling. Ensure order service doesn't directly access product database. Instead, it asks catalog service for product details via an API. Autonomy. Inventory service can choose to use a NoSQL database for speed, while payment service might rely on a traditional relational database for transaction integrity. Both teams can deploy independently. Resilience. If the recommendations service, which calls an external ML API, becomes slow or fails, the main shopping experience should still function, perhaps just without personalized recommendations. A circuit breaker pattern would prevent cascading failures. Observability. All services push logs to a central system. A request ID is passed through all service calls, so a single customer purchase can be traced from their browser all the way to the payment gateway. Conway's Law established dedicated teams for catalog team, order team, etc., each owning its respective services end-to-end. These principles form the bedrock of building successful microservices. They guide the decomposition of your application, the shape of your services, and the operational considerations necessary for them to thrive in a distributed environment. In the next chapter, we will delve deeper into the most crucial principle for service decomposition: domain-driven design and bounded contexts. Chapter 5, Domain-driven design. The bounded context approach. In the previous chapter, we introduced bounded context as a critical principle for drawing microservice boundaries. Now, we dive deeper into this powerful concept, which originates from domain-driven design, DDD. While DDD is a comprehensive software development methodology in itself, understanding its core tenets, particularly the bounded context, is indispensable for successfully decomposing monolithic applications into meaningful microservices. Mistakes in defining service boundaries are among the most common and costly errors in microservices adoption. DDD provides the intellectual framework to make these decisions effectively. Deep dive into domain-driven design, DDD. DDD, championed by Eric Evans in his seminal book, Domain-Driven Design, Tackling Complexity in the Heart of Software, is an approach to software development that focuses on modeling business knowledge within software. It aims to put the problem domain at the center of the development effort, using a rich, expressive model of that domain. Two key concepts from DDD are particularly relevant to microservices. Ubiquitous language. This is a language structured around the domain model and used by all team members, developers, domain experts, and other stakeholders. It includes terms and definitions that are unambiguous and consistent throughout the bounded context. Using this shared language helps prevent misunderstandings and ensures everyone is on the same page about the business concepts being implemented in the software. For example, in an e-commerce context, everyone should agree on what constitutes an order, a line item, or a customer. Domain model. This is an object-oriented model of a domain's concepts, their relationships, behaviors, and constraints. It's the heart of the software, where the business logic resides. In DDD, the model is not just a data schema. It's a living representation of reality that drives the application's functionality. DDD distinguishes between strategic design and tactical design. Strategic design focuses on the larger picture, identifying core domains, bounded contexts, and their relationships. Tactical design focuses on the detailed implementation within a single bounded context, dealing with aggregates, entities, and value objects. For microservices, strategic design, especially bounded contexts, is paramount for initial decomposition. The bounded context, your microservice blueprint. As discussed in Chapter 4, a bounded context defines a particular area of a system with its own explicit boundaries: language, ubiquitous language, and domain model. Within these boundaries, terms have specific, unambiguous meanings. Outside, those same terms might mean something entirely different or not exist at all. Why is it crucial for microservices? The core idea is that each microservice should align with and encapsulate a single bounded context. This provides a natural and powerful way to determine where one service ends and another begins. By doing so, you achieve autonomy. Each service has a clear responsibility and an independent internal model. Cohesion. All elements within the service are highly related to its specific domain. Loose coupling. Services communicate by collaborating across their boundaries, typically via explicit APIs, without needing to understand each other's internal domain models. Reduced cognitive load. Developers working within a service only need to understand the slice of the domain relevant to their bounded context. How to identify bounded contexts. Identifying bounded contexts is more of an art than a science, often involving collaboration between domain experts and developers. Here are some strategies. Look for distinct business capabilities. What are the major self-contained areas of your business? E.g., order fulfillment, customer relationship management, inventory management. Analyze ubiquitous language discrepancies. Pay close attention to words or concepts that have different meanings in different parts of the business. For example, a product in the marketing department might refer to a marketing campaign SKU, while in the warehouse, product refers to a physical item requiring inventory tracking. These are strong indicators of different bounded contexts. Identify organizational structure. As per Conway's law, existing organizational structures often reflect or should reflect natural domain boundaries. Seek out seams in a monolith. Where does your existing monolithic codebase naturally divide? What modules are highly coupled, and which ones have relatively independent concerns? Context mapping. Relationships between bounded contexts. Once you've identified your bounded contexts, and thus your potential microservices, the next step is to understand how they interact. Context mapping is a DDD technique for visualizing and defining the relationships between bounded contexts. These relationships dictate how microservices will communicate and integrate. Common relationship patterns include customer-supplier. One context, the customer, uses the model of another context, the supplier. The customer actively influences the supplier's development for its own needs. Example: order service customer relies on inventory service supplier to check stock. Partnering. Two contexts are tightly coupled and work closely together, sharing a common goal, often with shared ubiquitous language and potentially shared development cycles. This implies a higher degree of coordination. Example: billing service and subscription service in a SaaS product might be partners. Shared kernel. A small subset of the domain model or code is shared between two or more contexts. This reduces duplication but introduces coupling, so it should be used sparingly for truly stable, fundamental components. Conformist. One context, the conformist, simply adopts the model of another context, the upstream, without trying to translate or adapt it. This is often necessary when integrating with a third-party system that you cannot change. Example: integrating with a payment gateway where you must conform to their API. Anti-corruption layer, ACL. This is a translation layer that isolates one context from the quirks or complexities of another, often a legacy system. It prevents the corruption of your clean domain model by an older, less refined one. Example: when migrating features from a monolith, an ACL on the new microservice translates data from the old monolithic database into its new, clean domain model. This is key for the strangler fig pattern. Separate ways. Two contexts simply have no significant relationship. They don't need to communicate directly, perhaps because they serve entirely different business functions or audiences. Choosing the right communication pattern between services, to be discussed in Chapter 6, often depends on the context map. For instance, an anti-corruption layer might necessitate more complex data transformations, while a customer-supplier relationship could rely on simpler API calls. Aggregates and entities within a bounded context. Within a single bounded context, DDD further structures the domain model using concepts like entities and aggregates. These are critical for managing data consistency inside a service. Entities, objects defined by their unique identity rather than their attributes. For example, a customer or an order are entities, each having a unique ID. Value objects, objects that represent descriptive aspects of the domain and are defined by the equality of their attributes. They typically lack a persistent identity. For example, an address or a money amount could be value objects. Aggregates, a cluster of related objects, entities, and value objects that are treated as a single unit for data changes. An aggregate is a consistency boundary. Any changes within an aggregate must maintain internal consistency. It has a single aggregate root, which is the only object external clients should hold references to. Example: an order might be an aggregate root. Its constituent line items and shipping address would be part of its aggregate. You do not directly update a line item without going through the order aggregate root. This ensures that an order is always valid and consistent. For microservices, the significance of aggregates is that transactions and data consistency should ideally be confined within a single aggregate, and thus within a single microservice. Distributed transactions across multiple services are complex and generally avoided in favor of eventual consistency, often managed by patterns like sagas covered in Chapter 7. Practical example: breaking down an online bookstore. Let's apply these concepts to an online bookstore application. Initial thought: monolith. A single application with tables for books, customers, orders, payments, etc. Applying DDD/bounded contexts. Catalog context: ubiquitous language. Book, with title, author, ISBN, genre, book review, author. Service, catalog service. Responsibilities: managing book details, search, reviews, author information. Data: owns books, authors, reviews data. Inventory context: ubiquitous language. Stock item, focused on quantity, warehouse location, reservation. Service, inventory service. Responsibilities: tracking available stock, reserving items. Data, owns inventory data, SKUs, quantities, locations. Customer account context: ubiquitous language. Customer, account, wishlist, login. Service, customer account service. Responsibilities: user registration, login, profile management, wishlists. Data, owns customer and account data. Ordering context: ubiquitous language. Order, order item, cart. Service, order service. Responsibilities: creating orders from a shopping cart, managing order status. Data, owns order and line item data. An order would be an aggregate route here. Payment context: ubiquitous language. Transaction, payment method, refund. Service, payment service. Responsibilities: processing payments with external gateways, managing refunds. Data, owns transaction data. Shipping context: ubiquitous language. Shipment, tracking number, delivery address. Service, shipping service. Responsibilities: arranging shipments, providing tracking updates. Data, owns shipment and delivery data. Context map, simplified. Customer account service and catalog service are customers of each other for basic info. Order service is a customer of inventory service to check stock, and catalog service to get product details, and customer account service for customer details. Payment service is a supplier to order service. Shipping service is also a supplier to order service. This breakdown immediately reveals distinct services, each with its own responsibilities, data boundaries, and clear communication points. This is how you avoid the distributed monolith and build truly autonomous microservices. Common pitfalls: too many services, nanoservices. Oversegmenting leads to excessive communication overhead, complex deployment pipelines, and high operational costs. Focus on identifiable business capabilities. Too few services, mini monoliths. If your service still contains conflicting domain models or multiple distinct responsibilities, you haven't split enough. This leads back to coupling problems. Incorrect context boundaries. If a term's meaning constantly shifts within a service, or if two services frequently need to make deep internal assumptions about each other's data models, your boundaries are likely wrong. This will lead to constant refactoring and broken contracts. Analogy: specialized departments in a large company. Think of a large, successful company. It's not a single amorphous blob, it's divided into specialized departments: sales, marketing, finance, HR, R&D, logistics. Each department has its own clear purpose and responsibilities, its bounded context. Uses its own specialized vocabulary, ubiquitous language, e.g., sales funnel versus balance sheet. Manages its own data, e.g., sales has lead data, HR has employee records. No other department directly accesses another's internal spreadsheets. Communicates with other departments through well-defined processes and interfaces, e.g., sales submits an order to logistics, HR sends payroll info to finance. Can evolve its internal processes without disrupting other departments, as long as it adheres to its interfaces. This departmental structure mirrors the benefits and design principles of microservices based on bounded contexts. By applying DDD, you're not just breaking up code. You're structuring your software team and business functions into highly effective, independent, and collaborative units. In the next chapter, we will explore the critical aspect of how these independent services communicate with each other effectively. Chapter 6. Designing APIs and Communication in a Distributed World. Once you've successfully decomposed your application into microservices, each aligned with a specific business capability and operating within its own bounded context, the next critical challenge emerges. How do these independent services communicate with each other? In a distributed system, communication is no longer a simple function call within a single process. It involves network calls, serialization, and message protocols, which introduce latency, unreliability, and new failure modes. Effective interservice communication is paramount for a functional microservices architecture. Poorly designed communication can lead to tightly coupled services, performance bottlenecks, and a system that is difficult to debug and maintain. This chapter explores the primary communication patterns and technologies used in microservices, along with strategies for designing robust and flexible APIs. The two paradigms, synchronous versus asynchronous communication. Microservices communication broadly falls into two main categories. Synchronous communication. The client requesting service sends a request to the server responding service and waits for a response. The client is blocked until the response is received or a timeout occurs. Analogy, making a direct phone call. You speak, then wait for the other person to respond before continuing the conversation. If they don't pick up, you get a busy signal or voicemail. When to use? For operations that require an immediate response, such as querying data, e.g., getting product details, or performing real-time transactions where the success or failure of the operation is critical for the client to proceed. Beware of cascading failures. If one service in a synchronous chain is down, the whole chain breaks and tight coupling. Asynchronous communication. The client sends a message or event to a server and doesn't wait for an immediate response. The client continues its processing, and the message is handled independently by the recipient, often at a later time. A response, if needed, is delivered via a separate mechanism, e.g., another asynchronous message. Analogy. Sending a letter or an email. You send it, you don't wait for an immediate reply, and you continue with your day. The recipient processes it independently, and if they respond, it's a separate action. When to use? For operations where an immediate response is not required, background processing, event-driven architectures, or when high decoupling is desired. Examples include sending notifications, processing orders, or updating inventory. Benefits: increased resilience, sender not blocked by receiver; greater scalability, sender can send messages even if receiver is temporarily overloaded; loose coupling. Challenges: eventual consistency, debugging complexity, understanding flow across disparate messages, message ordering. Synchronous communication protocols. The most common choices for synchronous interservice communication are: 1. REST-TFL APIs, representational state transfer. REST remains the dominant architectural style for web services and is widely adopted for microservices. Principles. REST is built on standard HTTP methods: GET, POST, PUT, DELETE, stateless communication, and resource-based URLs. Resources are identifiable entities, e.g., /products/ID, /users/ID. Advantages: widely understood, uses standard HTTP infrastructure, language agnostic, good for human readability, using JSON XML. Disadvantages: can be chatty, multiple requests for related data, often leads to overfetching or underfetching of data. Best for request-response patterns for general data access and manipulation. 2. GraphQL. Principles: a query language for APIs and a runtime for fulfilling those queries with your existing data. Allows clients to request exactly the data they need, no more, no less, in a single request. Advantages: reduces overfetching, underfetching, minimizes network requests, strong typing, better for evolving APIs. Disadvantages: can introduce complexity on the server side, requires a client-side library to compose queries. Best for complex data aggregation for clients, especially front-ends, where flexibility in data retrieval is paramount. 3. gRPC, Google Remote Procedure Call. Principles: a high-performance, open-source universal RPC framework. It uses protocol buffers, protobuf, as its interface definition language, IDL, and underlying message interchange format. Advantages: extremely fast, uses HTTP2 and protobuf for efficient serialization. Language agnostic, code generation for many languages. Supports streaming, client, server, bidirectional. Disadvantages: less human-readable than JSON, requires code generation, steeper learning curve. Best for high-performance, low-latency inter-service communication, polyglot environments, streaming data. When choosing a synchronous protocol, consider performance needs, team familiarity, and the complexity of your data models. For most CRUD, create, read, update, delete operations, REST is a solid, well-understood choice. For complex client-side data needs, GraphQL shines. For high-throughput, internal-only communication, gRPC excels. Asynchronous communication protocols and patterns. Asynchronous communication is fundamental for achieving true loose coupling and resilience in microservices. One-message queues point-to-point. Mechanism: a sender-producer puts a message onto a queue and a receiver-consumer retrieves it. Each message is consumed by only one consumer. Products: RabbitMQ, Apache ActiveMQ, Amazon SQS, Simple Queue Service. Advantages: decoupling: sender doesn't need to know about receiver. Load balancing across multiple consumers, buffering handles spikes. Reliability: messages persistent until consumed. Best for work queues, background job processing where order might be important, but immediate response is not. 2. Publish-subscribe, pub-sub. Mechanism: a sender-publisher broadcasts messages to a topic or exchange. Any number of receivers, subscribers, that are interested in that topic receive a copy of the message. Products: Apache Kafka, RabbitMQ, using exchanges, Amazon SNS, Simple Notification Service, Google Cloud Pub-Sub. Advantages: high decoupling, publisher knows nothing about subscribers. Highly scalable, many consumers can process messages concurrently. Enables event-driven architectures. Best for event broadcasting, data streaming, enabling multiple services to react to a single event without direct knowledge of each other. 3. Event-driven architecture, EDA. EDA is more of an architectural style, built around asynchronous communication. Services emit events, facts that something notable happened when their state changes, and other services react to these events. Example: an order service might publish an order-created event. The inventory service subscribes to this to decrement stock, the customer service subscribes to send a confirmation email, and the payment service subscribes to initiate payment. Benefits: extreme decoupling, clear audit trails, promotes eventual consistency, highly scalable and resilient. Challenges: debugging asynchronous flows can be tricky, managing eventual consistency requires careful design, message ordering can be critical and complex. Service discovery: how services find each other. In a dynamic microservices environment, service instances are constantly appearing, disappearing, or changing their network locations, e.g., due to scaling up-down, deployments, or failures. Services need a reliable way to find each other. This is where service discovery comes in. Client-side discovery. The client service is responsible for querying a service registry, e.g., Eureka, HashiCorp Console, Zookeeper with Curator, or even a basic DNS record, to get the network locations of available instances of a target service. The client then load balances across these instances. Advantages: simpler infrastructure, direct client control over load balancing. Disadvantages: client needs to implement discovery logic, client-specific libraries required. Server-side discovery. The client service makes requests to a router, load balancer, or API gateway. This intermediary then queries the service registry and forwards the request to an available service instance. Platforms providing this: cloud-based load balancers, Oz ELB, Azure Load Balancer, and most notably, Kubernetes. Kubernetes' built-in DNS and service objects provide server-side discovery and load balancing seamlessly. Advantages: clients don't need discovery logic, simpler for developers, abstract infrastructure. Disadvantages: requires an additional network hop, may introduce a central point of failure if not well managed. For microservices deployed on platforms like Kubernetes, server-side discovery is typically handled automatically through Kubernetes' native service and DNS mechanisms, greatly simplifying the developer's life. API gateways, the single entry point. An API gateway acts as a single entry point for all external client requests into the microservices system. Instead of clients having to know about and call multiple backend services directly, they interact only with the gateway. Key functions of an API gateway: request routing. Directs incoming requests to the appropriate microservice based on the URL path, HTTP method, or other criteria. Request aggregation. For complex client UIs that need data from multiple services, the API gateway can fan out a single request to multiple backend services, aggregate their responses, and return a single, tailored response to the client. This avoids chatty communication between client and backend. Authentication and authorization. Centralizes security concerns. The gateway can authenticate external clients and then forward security credentials or contextual information, e.g., user ID, roles, to downstream services using internal high-trust mechanisms. This offloads authentication from individual microservices. Rate limiting. Protects backend services from being overwhelmed by too many requests from a single client. Protocol translation composition. Can translate between external protocols, e.g., REST from a mobile app, and internal microservice protocols, e.g., gRPC. Centralized logging monitoring. Can collect valuable metrics and logs for all incoming external traffic. When to use, when to avoid. API gateways are invaluable for complex systems dealing with diverse external clients. However, they can become a performance bottleneck or a monolithic single point of failure if not designed and managed carefully. They should selectively handle cross-cutting concerns, not replicate all business logic. Contract-first design and versioning. In a world of multiple independent services, clear API contracts are essential. The contract defines how a service can be called, what data it expects, and what data it returns. Using tools like OpenAPI, Swagger, for REST APIs or protocol buffers for gRPC, enables a contract-first approach, where the API definition is established and agreed upon before implementation. This allows client and server development to proceed in parallel and facilitates automatic code generation. API versioning. As services evolve, their APIs will inevitably change. Strategies for managing these changes are crucial to avoid breaking existing clients. URL versioning, v1 products, v2 products. Simple, but can lead to long URLs. Header versioning. Using a custom HTTP header, e.g., XAPI version 1. Cleaner URLs but less discoverable. Content negotiation. Using the accept header to request a specific media type, e.g., application/vndmycompany v1 plus JSON. Backwards compatibility. The ideal approach, where new versions are strictly additive and don't change or remove existing fields' behavior, allowing old clients to continue working with the new service. For breaking changes, minor version bumps, v1.1 to v1.2, or major version bumps, v1 to v2, are common. Supporting older versions for a grace period before deprecation is a common practice. Practical application. A user onboarding flow. Let's illustrate with a communication flow for a user onboarding process. Client web browser, API gateway. User submits registration form. API gateway authenticates the request and routes it to the user registration service. User registration service, synchronous. Auth service. User registration service makes a synchronous REST call to auth service to create the user's login credentials. User registration service, asynchronous publish. Message broker. Once the user account is created, user registration service publishes a user-registered event to a Kafka topic. It does not wait for a response. Notification service, asynchronous subscribe. Message broker. Notification service subscribes to user-registered events and sends a welcome email and SMS to the new user. Analytics service, asynchronous subscribe. Message broker. Analytics service also subscribes to user-registered events to update user metrics and perform initial segmentation. User profile service, asynchronous subscribe. Message broker. User profile service subscribes to user-registered events to create a default user profile. This flow combines synchronous calls, where an immediate response is needed, like creating login credentials, with asynchronous events for decoupled, non-urgent actions like sending notifications or updating analytics. The API gateway provides a single, secure entry point, and the message broker ensures resilience and scalability for subsequent actions. Conclusion: designing effective communication around your microservices is a nuanced art. It requires a deep understanding of synchronous and asynchronous patterns, careful API design, strategies for discoverability, and a clear approach to versioning. Done well, it fosters autonomy, resilience, and scalability. Done poorly, it can quickly turn into a tangled, fragile mess. By thoughtfully applying these principles and choosing the right tools for the job, you can ensure your microservices architecture communicates smoothly and reliably, paving the way for advanced practices like distributed data management, which we tackle in the next chapter. Chapter 7, Managing Data, the Distributed Database Challenge. One of the most profound shifts when moving from a monolithic application to a microservices architecture lies in data management. In a monolith, a single, central database typically serves all components. While this simplifies data consistency and transactional integrity, it also becomes a bottleneck and a point of tight coupling. In a microservices world, data management becomes distributed, introducing new complexities and demanding a reevaluation of traditional database paradigms. This chapter delves into the strategies and challenges of managing data across multiple, independent microservices, focusing on how to maintain consistency, handle queries, and manage distributed transactions. The database per service pattern. The cornerstone of data management in microservices is the database per service pattern. This principle dictates that each microservice should own its own dedicated database. No other service should directly access another service's database. All communication with a service's data must go through its public API. Analogy: imagine a company building. In a monolith, all departments dig through the same central filing cabinet. In a microservices company, each department has its own locked filing cabinet. If the sales team needs customer details from the customer service department, they don't break into customer service's filing cabinet. They ask the customer service department, which then provides the information through its established procedures. Advantages of database per service. Autonomy. A service can evolve its data model independently without impacting other services. This greatly enhances independent deployability. Technology diversity, polyglot persistence. Each service can choose the best type of database for its specific needs. A product catalog service might use a NoSQL document database for flexible schema and fast reads. A payment service might require a traditional relational database for strong transactional integrity. Improved fault isolation. If one service's database experiences issues, it doesn't necessarily bring down other services. Decoupling prevents the shared database anti-pattern, which can become a silent monolith and destroy the autonomy benefits of microservices. Disadvantages of database per service. Distributed transactions are hard. Maintaining atomicity, consistency, isolation, durability, properties across multiple databases is extremely challenging and generally avoided. Data duplication. Some data might logically appear in multiple services, e.g., a customer ID in order service and shipping service. This requires careful management to avoid inconsistencies. Queries across services are complex. Joining data across different services' databases is not straightforward. Data models and heterogeneity, polyglot persistence, the ability to choose different database technologies for different services is known as polyglot persistence. This means a single microservices application can utilize a mix of relational databases, e.g., PostgreSQL, MySQL, NoSQL databases, e.g., MongoDB, Cassandra, DynamoDB, graph databases, e.g., Neo4j, or even specialized search engines, e.g., Elasticsearch. Choosing the right database. Relational databases, SQL. Best for applications requiring strong transactional consistency, complex joins, and structured data, such as payment service, inventory service for precise counts. Document databases, NoSQL. Flexible schema, good for semi-structured data, often scales horizontally well. Suitable for product catalog service or user profile service. Key value stores. Very fast reads writes by key, simple data model. Useful for caching or session management in services like auth service. Graph databases. Ideal for representing and querying complex relationships, such as recommendation service or social network service. Search engines. Optimized for full-text search, aggregation, and analytics, like a dedicated search service. The flexibility of polyglot persistence allows each service to optimize its data storage for its specific access patterns and consistency requirements. Challenges of distributed data. With each service having its own database, new challenges arise. One, data consistency, from ACID to base. In traditional monolithic systems, ACID transactions ensure immediate consistency across all related data. In a distributed microservices environment, achieving global ACID consistency across multiple services is prohibitively complex and often detrimental to performance and availability. Instead, microservices architectures typically rely on base properties. Basically available. The system guarantees availability for the requests, but response might be stale. Soft state. The state of the system may change over time, even without input, eventually becoming consistent. Eventual consistency. The system will eventually become consistent, given a period of time when no new updates are made. When to choose what? Strong consistency, ACID, required for critical financial transactions, e.g., debiting a bank account, or inventory where precise counts are crucial. These operations should typically be confined within a single service's transaction boundary. Eventual consistency, base, suitable for most other operations where immediate consistency across the entire system is not strictly necessary, and waiting a short period for data to propagate is acceptable. This is the norm in microservices communication using asynchronous events. 2 queries across services. How do you get data that logically spans multiple services? For example, showing a user's recent orders from order service along with the product details from product catalog service. You cannot directly join tables across services. Common patterns include API composition. The client, e.g., a front-end application or an API gateway, makes multiple calls to different services and then combines the responses. Example: client calls get orders from order service to get order IDs, then calls get/product/ID for each product ID from product catalog service. This can be chatty. Data replication/denormalization, read replicas materialized views. For frequently accessed, cross-service data, a service might maintain a read-only, denormalized copy of data owned by other services. This copy is updated asynchronously via events. Example: search service might subscribe to product-updated events from product catalog service to update its internal search index. The customer service might subscribe to order-created events to update a total orders count for a customer. Benefits: fast reads, reduced cross-service calls for queries. Challenges: potential for stale data, eventual consistency, increased storage, complexity of keeping replicas in sync. GraphQL federated queues. As discussed in Chapter 6, GraphQL's ability to query data from multiple backend services and combine it into a single response is powerful for complex data requirements. 3. Distributed transactions, avoiding two-phase commit. Traditional distributed transactions, like two-phase commit, are notoriously complex, slow, and prone to blocking. They are generally avoided in microservices, as they create tight coupling and reduce availability. Instead, the saga pattern is preferred. Saga pattern. A saga is a sequence of local transactions where each transaction updates data within a single service. If a local transaction fails, the saga executes compensating transactions to undo the changes made by previous successful transactions. Sagas ensure eventual consistency across multiple services. There are two main ways to coordinate sagas. Choreography-based saga. Each service produces events, and other services listen to these events and perform their own local transactions, potentially triggering further events. There's no central coordinator. Analogy: a dance floor where each dancer reacts to the moves of others. Benefits: simpler to implement for simple sagas, no single point of failure. Challenges: hard to understand the end-to-end flow, debugging can be difficult, managing complex rollback logic. Orchestration-based saga. A central orchestrator service coordinates all the local transactions of the different participant services. The orchestrator tells each participant what to do, waits for confirmation, and decides the next step. Analogy: a conductor leading an orchestra. Benefits: clear end-to-end flow, easier to debug and manage complex compensation logic. Challenges: the orchestrator service can become a single point of failure or a bottleneck if not designed to be stateless scalable itself. Practical example: order fulfillment saga. Let's trace an order fulfillment process involving an order service, inventory service, and payment service using a choreography-based saga. Order service receives a new order. Local transaction creates the order in its database with status pending. Emits event publishes order created event to a message broker. Inventory service subscribes to order created events. Local transaction attempts to reserve items in its database. If successful, publishes inventory reserved event. If failed, e.g. out of stock, publishes inventory reservation failed event. Payment service subscribes to inventory reserved events. Local transaction attempts to charge the customer. If successful, publishes payment processed event. If failed, publishes payment failed event. Order service subscribes to inventory reservation failed, payment failed, and payment processed events. If inventory reservation failed or payment failed, local transaction updates order status to cancelledicumpnsatng. Emits compensating events, e.g., order canceled event for inventory service to unreserve. If payment processed, local transaction updates order status to completed. Emits event, order completed. This saga ensures that even if one step fails, the system can revert to a consistent state through compensating actions, ensuring eventual consistency. Event sourcing, brief overview. Event sourcing is an advanced data management technique where, instead of storing the current state of an application, you store a sequence of immutable events that led to that state. The current state is then derived by replaying these events. Benefits: provides a complete audit trail, supports complex temporal queries, enables powerful event-driven architectures. Challenges: more complex to implement, requires different querying patterns. Relevance to microservices. Event sourcing often complements sagas and can be used within a single service to manage its own data lifecycle. Data migration strategies. Changing a service's data model in a microservices environment requires careful planning, especially if the service's API is consumed by other services or external clients. Backward compatibility, the golden rule. Try to make schema changes additive, add new columns, don't remove or rename existing ones, so older versions of your service or its consumers can still function. Database refactoring/migration tools. Use database migration tools, e.g., Flyway, Liquibase, to manage schema changes and versioning for each service's database. Dual write, dual read. During a complex migration where data format changes, write to both old and new formats, dual write, then read from both, dual read, eventually phasing out the old format. Versioned APIs. As discussed in Chapter 6, for breaking changes, you might need to introduce a new API version. Anecdote: the shared customer database. A mid-sized tech company, let's call them Legacy Tech, decided to move to microservices. They successfully split their application into auth service, profile service, subscription service, and notification service. However, to accelerate the migration, they decided to keep a single, massive customer database that all new services would query directly. It was supposed to be temporary, explained their lead architect, just to get us going. But then, the profile service team wanted to add a preferred time to contact field. They added it to the shared customer table. The notification service team, which also read from customers, wasn't explicitly notified, and their old SQL queries started throwing errors because of the new column they didn't expect. Then, the subscription service team changed an active flag from an integer to a Boolean, and suddenly, authentication failed because auth service couldn't parse it. What happened? Legacy tech had inadvertently created a silent monolith. Their services might have been separate processes, but they were still tightly coupled through the shared database schema. Any change to the database required careful, manual coordination across all teams consuming that database, effectively nullifying the independent deployability benefit of microservices. They soon realized that the database per service pattern was not a suggestion. It was a fundamental requirement for true microservice autonomy. Conclusion: managing data in a microservices architecture is arguably its greatest complexity. The shift from a single, centralized database to distributed, autonomous data stores for each service introduces challenges around consistency, querying, and transactions. By embracing the database per service pattern, understanding eventual consistency, leveraging the Saga pattern for cross-service transactions, and carefully designing data access and replication, organizations can navigate this distributed data landscape effectively. These foundational choices in data management lay the groundwork for how you deploy and operate your services, which is the focus of our next chapter. Chapter 8: Deployment Strategies. From containers to orchestration. You've designed your microservices, defined their boundaries, established communication patterns, and tackled data management. Now, how do you actually get them running in production? Moving from a single, monolithic application to dozens or even hundreds of independently deployable services introduces significant challenges in terms of deployment, scaling, and operational management. This chapter explores the modern tools and practices, primarily containers and orchestrators, that make operating microservices at scale both feasible and efficient. The container revolution, Docker basics. Before the widespread adoption of containers, deploying applications often involved provisioning virtual machines, VMS, or bare metal servers. Each required careful configuration of operating systems, libraries, and dependencies, often leading to works on my machine syndrome and inconsistencies between development, testing, and production environments. Containers revolutionized software deployment by providing a lightweight, portable, and consistent packaging mechanism. A container bundles an application and all its dependencies, libraries, configuration files, environment variables, runtime, into a single, isolated unit. What are containers? Unlike virtual machines, which virtualize the entire hardware layer and each run a full operating system, containers share the host operating system's kernel. They provide process and file system isolation, making them much lighter, faster to start, and more resource efficient than VMs. Key Docker concepts. Dockerfile, a text file containing instructions for building a Docker image. It specifies the base OS, dependencies, application code, and how to run the application. Image, a lightweight, standalone, executable package of software that includes everything needed to run an application. Code, runtime, system tools, system libraries, and settings. Images are immutable. Container, a runnable instance of a Docker image. You can start, stop, move, or delete a container. Multiple containers can run on the same machine, isolated from each other. Benefits of containerization for microservices. Portability. A containerized microservice runs consistently across different environments, developer's laptop, testing server, cloud production, because it carries its entire environment with it. Isolation. Each microservice runs in its own isolated container, preventing conflicts between dependencies and ensuring that one service doesn't negatively impact another on the same host. Consistency. The build process creates an immutable image, guaranteeing that the same code and dependencies are deployed every time, reducing works on my machine issues. Faster startup. Containers start much quicker than VMS, enabling rapid scaling and efficient resource utilization. Docker became the de facto standard for containerization, making it easy to build, ship, and run any application as a lightweight, portable container. Continuous integration and continuous delivery. CI/CD for microservices. The promise of independent deployability in microservices can only be fully realized with robust continuous integration, CI, and continuous delivery, CD, pipelines. Continuous integration. Developers frequently integrate their code changes into a central repository. Automated builds and tests run, quickly detecting integration errors. For microservices, each service typically has its own CI pipeline. Continuous delivery. Code changes that pass automated tests are automatically prepared for release to production. This means the software is always in a deployable state. In a microservices context, this often means that each microservice has its own independent CD pipeline, allowing it to be released whenever it's ready without waiting for others. Key aspects of CI/CD for microservices: automated builds and tests. Every code commit triggers an automated build of the container image and runs unit, integration, and other relevant tests. Independent pipelines. Each microservice has its own dedicated CI/CD pipeline. This is critical for achieving independent deployability. A new version of the payment service can be released without needing to rebuild or retest the product catalog service. Artifact management. Container images and other deployable artifacts are stored in a versioned repository, e.g., Docker registry, Google Container Registry. Feature flags/dark launches. To decouple deployment from release, features can be deployed but hidden behind feature flags. This allows new code to be deployed to production, tested with a small subset of users, dark launch, and then activated for all users without another deployment. Container orchestration, Kubernetes foundations. While containers solve the problem of packaging and running individual microservices, managing dozens or hundreds of containers across a cluster of machines is complex. This is where container orchestration platforms come in. They automate the deployment, scaling, management, and networking of containerized applications. Kubernetes, often abbreviated as K8s, has emerged as the undisputed leader in container orchestration. It provides a robust, extensible framework for managing distributed workloads and services. Why orchestration? Automated deployment. Deploy containerized applications with declarative configurations. Scaling. Automatically scale services up or down based on load or predefined rules. Self-healing. Automatically restarts failed containers, replaces unhealthy ones, and reschedules containers on healthy nodes. Service discovery and load balancing. Provides built-in mechanisms for services to find each other and distribute network traffic among service instances. Resource management. Efficiently allocates compute, memory, and storage resources across a cluster. Configuration management and secret management. Securely injects configuration and sensitive data into containers. Key Kubernetes concepts, simplified for microservices. Pod, the smallest deployable unit in Kubernetes. A pod typically contains one or more tightly coupled containers that share network and storage resources. For microservices, typically each microservice runs in its own pod, often a single container within that pod. Deployment, a higher-level object that manages pods. You define the desired state, e.g., run 3 instances of product catalog service. The deployment controller ensures that this state is maintained, handles rolling updates and rollbacks. Service, an abstract way to expose an application running on a set of pods as a network service. It provides a stable IP address and DNS name for the pods it manages, acting as an internal load balancer. This is crucial for service discovery. Namespace, a way to logically partition a Kubernetes cluster into virtual subclusters. Used to isolate resources and teams, e.g., development, staging, production namespaces, or namespaces per team. Benefits of Kubernetes for microservices. Abstraction of infrastructure. Developers focus on their application code and container image. Kubernetes handles the underlying infrastructure intricacies. Mature ecosystem. A vast and rapidly evolving ecosystem of tools and integrations for networking, storage, security, observability, and more. Portability across clouds. Kubernetes can run on various public clouds, Oz EKS, Azure AKS, Google GKE, on-premise, or bare metal, providing consistency. Complexity. While powerful, Kubernetes has a steep learning curve. Setting up and managing a production-grade cluster requires specialized knowledge. Cloud providers offer managed Kubernetes services, EKS, AKS, GKE, to reduce this operational burden. Deployment patterns. Even with container orchestration, how you deploy updates to your microservices is critical to minimize downtime and risk. Rolling updates, the default and most common strategy. New versions of services are gradually rolled out, replacing old instances one by one. Traffic is automatically shifted to new instances without downtime. If an issue is detected, the rollout can be paused or rolled back. Mechanism. Kubernetes deployments support rolling updates natively. Blue-green deployments. 2 identical production environments are maintained. Blue, the current live version, and green, the new version. Traffic is initially directed to blue. Once green is fully deployed and tested, all traffic is quickly switched over from blue to green. If problems arise, traffic can be instantly switched back to blue. Advantages. Near-zero downtime for users, fast rollback. Disadvantages. Requires twice the infrastructure, can be complex to manage database migrations across environments. Canary releases. A new version of a service, Canary, is deployed to a small subset of servers and receives a small percentage of live traffic, e.g., 5 to 10%. This allows real-world testing of the new version with minimal impact. If successful, the new version is gradually rolled out to more servers. If not, it's rolled back. Advantages. Reduces risk of widespread failures, allows early detection of performance or functional issues. Disadvantages. Requires sophisticated traffic routing and monitoring, can take longer to fully deploy. Tools. Service meshes, like Istio, API gateways, or load balancers can manage traffic splitting for Canary releases. Infrastructure as code, IAC. A crucial practice for managing microservices deployments at scale is infrastructure as code, IAC. Instead of manually configuring servers, networks, and deployments, you define your infrastructure and configuration in code, typically in declarative format files like YAML or JSON. Benefits. Automation. Eliminates manual errors and ensures consistent environments. Version control. Infrastructure definitions are versioned and can be tracked in source control, just like application code. Reproducibility. Easily recreate environments. Development, test, production. Documentation. The code itself serves as living documentation of your infrastructure. Tools. Terraform multi-cloud, AWS CloudFormation, Azure Resource Manager, ARM, templates, Kubernetes YAML configuration files. Practical considerations. Minimize container size. Lean images, e.g., using Alpine Linux base images, multi-stage Docker builds, reduce build times, deployment times, and attack surface. Managing secrets. Never hardcode sensitive information, API keys, database credentials, in container images or configuration files. Use secret management tools like Kubernetes Secrets, HashiCorp Vault, or Cloud Provider Secret Services. Resource limits. Define CPU and memory limits for your containers within Kubernetes to prevent a single misbehaving service from consuming all resources on a node. Case study. QuickShip Delivery. QuickShip Delivery, a rapidly growing logistics company, was struggling with their monolithic delivery management system. Every small change to the routing algorithm meant a full redeployment, leading to disruptions. They transitioned to microservices, and Kubernetes became their backbone. Before Kubernetes, explained Maya, QuickShip's head of engineering, deploying a hotfix was an all-hands-on-deck, sweating bullets operation. Now, our route optimization service team can push an update multiple times a day. We containerize it with Docker. Our CI pipeline automatically builds the image and runs tests, and then Kubernetes handles the rolling update. If something goes wrong, we can roll back in minutes. She continued, the real game changer was how independent teams became. The driver app team can iterate on features, and as long as their service respects the API contracts, they don't have to coordinate every deployment with the customer notification team. Kubernetes' self-healing capabilities also mean we sleep better at night. If a node goes down, Kubernetes automatically reschedules affected pods on healthy nodes. It's truly transformed our operational agility. QuickShip uses a combination of rolling updates for minor changes and blue-green deployments for major, riskier updates, ensuring their critical delivery services remain available 24/7. Their infrastructure setup is entirely managed by ISC, allowing them to spin up new environments for testing in minutes. Conclusion: deploying and managing microservices fundamentally shifts the operational paradigm from static server management to dynamic, automated orchestrations. Containers provide the ideal packaging for microservices, ensuring consistency and portability. Orchestration platforms like Kubernetes then automate the complex tasks of deployment, scaling, healing, and networking at scale, making independent service management a reality. By combining these technologies with robust CI/CD practices and infrastructure as code, organizations can achieve the high velocity, resilience, and agility that microservices promise. However, running a distributed system also means that you need to know what's happening inside it all the time. That's the topic of our next chapter, observability. Chapter 9, the pillars of operability: logging, monitoring, and tracing. Imagine you've successfully built a sprawling city out of Lego blocks, your microservices, each block meticulously designed and deployed. But what happens if a building catches fire or a road collapses? In a simple, single-building town, a monolith, you'd spot the problem quickly. In a complex city, you need a sophisticated emergency response system. This is where operability comes in for microservices: the ability to keep your distributed system running smoothly, identify issues quickly, and diagnose problems effectively. Operability relies on three crucial pillars: logging, monitoring, and distributed tracing. Without these, operating a microservices architecture is like flying an airplane in dense fog without instruments. You simply can't tell what's going on until it crashes. The challenge of operability in distributed systems. In a monolithic application, all events, errors, and performance data typically reside within a single process or a handful of interconnected ones. Debugging often involves inspecting a single log file or attaching a debugger to one process. In a microservices world, this changes dramatically. Many independent services. A single user request might traverse dozens of microservices, each running on a different server, written in a different language, and maintaining its own logs. Asynchronous communication. Events might be processed hours after they're initiated, making a linear request flow difficult to follow. Dynamic environments. Services are constantly scaling, being deployed, or even failing, meaning their physical location and instances change frequently. Due to these complexities, traditional observability tools fall short. You need comprehensive solutions that can collect, aggregate, analyze, and visualize data from across your entire distributed system. Pillar 1. Logging. Logging is the practice of recording significant events that occur within an application. These events provide forensic evidence about what happened, when, and potentially why. Centralized logging. The most crucial aspect of logging in microservices is to centralize all logs. Do not simply leave logs on individual service instances. Tools like the Elk Stack, Elasticsearch, Logstash, Kibana, Splunk, or cloud-native solutions, e.g. AWS CloudWatch, Google Cloud Logging, Azure Monitor, ingest logs from various sources, making them searchable and analyzable from a single interface. Structured logging. Instead of unstructured text logs, user X did Y, use structured logging, e.g. JSON format. This adds machine-readable context, e.g. level, info, timestamp, service. Order service, userid, 123, orderid, ABC, message, order created. Structured logs enable powerful queries, filtering, and aggregation. Contextual logging. For a distributed system, this is paramount. Every log entry related to a specific interaction should carry a correlation ID, also known as a request ID or TRACID. This ID is generated at the very beginning of a request, e.g., at the API gateway, and passed along to every service that processes the request, whether synchronously or asynchronously. If a user reports an issue, you can simply search for their correlation ID in your central log system and see the entire flow across all services involved. Logging best practices. What to log. Errors, warnings, successful key operations, security-relevant events, and context for debugging. Avoid logging overly verbose debug messages in production unless needed for specific troubleshooting. Log levels. Use standard log levels, debug, info, warn, error, fatal consistently. Sensitive data. Never log sensitive information, passwords, PII, credit card numbers. Pillar 2. Monitoring. Monitoring is the continuous observation of system health, performance, and behavior. While logs tell you what happened, metrics, the output of monitoring, tell you how well your services are performing right now and how their performance trends over time. Why monitor? Health checks. Determine if a service is alive and ready to receive traffic. Performance metrics. Understand latency, throughput, error rates, resource utilization, CPU, memory, disk I/O, network. Alerting. Proactively notify operations teams when predefined thresholds are breached, e.g., error rate exceeds 5%, latency spikes. Capacity planning. Understand resource trends to plan for future scaling. Types of metrics in microservices. Infrastructure metrics. CPU usage, memory, network I/O, disk space for the underlying nodes. Application metrics, specific to your microservices, request level metrics. Latency, throughput, error rates per API endpoint. Business metrics, orders per minute, successful registrations, items added to cart. These are invaluable for business stakeholders. Service-specific metrics. Queue depths, cache hit rates, database connection pool usage. Golden signals. For any service, focus on these 4 signals. Latency, the time it takes to serve a request. Traffic, how much demand is being placed on your service. Errors, the rate of requests that fail. Saturation, how full your service is. Monitoring tools. Prometheus, a popular open-source monitoring system with a powerful query language, PromQL, ideal for time series data. Well-suited for Kubernetes environments. Grafana, a leading open-source platform for visualizing metrics, often used in conjunction with Prometheus to create rich, interactive dashboards. Datadog, New Relic, Dynatrace. Commercial all-in-one solutions that combine metrics, logs, and tracing capabilities. Built-in cloud services, AWS CloudWatch, Google Cloud Monitoring, Azure Monitor. Alerting strategies, actionable alerts. Alerts should clearly indicate what's wrong and ideally provide context for resolution, rather than just raw numbers. Reduce alert fatigue. Thresholds, define clear thresholds for when an alert should fire. Response mechanisms. Integrate alerts with notification systems, email, Slack, PagerDuty to reach the right people promptly. Pillar 3, distributed tracing. While logs give you detailed events and metrics provide aggregated insights, distributed tracing allows you to see the end-to-end journey of a single request as it propagates through multiple services in your distributed system. The challenge: a customer clicks buy now. This might involve web app, order service, inventory service, payment service, notification service, and shipping service. If the request is slow, how do you know which service is the bottleneck? How tracing works: each operation within a service is called a span. Spans are organized into a trace, which represents the end-to-end request. Each span records its operation name, start-end times, and contextual data, e.g., service name, endpoint, request ID. Crucially, each span includes a tracid, the correlation ID from logging, and a spanid. When one service calls another, it passes its tracid and its own spanid as the parented for the new span. This creates a causal chain that reconstructs the request's path. Benefits of distributed tracing. Root cause analysis. Quickly identify the exact service and operation responsible for latency or errors. Performance bottleneck identification. Pinpoint which parts of your system are slowing down requests. Service dependency mapping. Visualize how services interact. Better understanding of flow. For complex, asynchronous interactions, tracing provides invaluable insights into message flows. Tracing tools. Jaeger and Zipkin, popular open-source distributed tracing systems. OpenTelemetry. a vendor-neutral open-source project that provides a standardized set of APIs, SDKs, and tools for instrumenting, generating, and exporting telemetry data, traces, metrics, and logs. It's rapidly becoming the industry standard. Commercial APM tools, Datadog, New Relic, Splunk APM, Dynatrace often include tracing, dashboards, and alerting. Actionable insights. Bringing logs, metrics, and traces together into custom dashboards provides a consolidated view of your system's health. Dashboards. Create dashboards tailored to different audiences, e.g., engineering, product, business. Visualizations help quickly spot trends, anomalies, and potential issues. Application Performance Management, APM. Many commercial tools offer integrated APM solutions that combine all these pillars into a single platform, often with AI-driven insights and anomaly detection. Chaos engineering, brief introduction. Beyond passive observation, chaos engineering is the discipline of experimenting on a distributed system to build confidence in its ability to withstand turbulent conditions in production. It involves deliberately injecting faults, e.g., network latency, service failure, resource exhaustion, into the system in a controlled manner to identify weaknesses before they cause real-world outages. This proactive approach complements the 3 pillars of operability by testing your monitoring, alerting, and recovery mechanisms outside of a crisis. Practical example: troubleshooting a slow API response. A user complains that their order history page is taking too long to load. Here's how you'd use the 3 pillars to diagnose. Monitoring. You check your application dashboards. You notice that the order retrieval service shows a spike in P99 latency, 99th percentile latency, around the time the user reported the issue. The error rate is still low, but response times are high. Distributed tracing. You go to your tracing system, search for traces related to the order retrieval service within the affected time frame. You find traces where the order retrieval service itself is fast, but it's making a call to payment service that's taking an unusually long time. You drill down into that specific trace and see the payment service's internal database query span is extremely long. Logging. With the traced from the slow transaction identified by the tracing system, you go to your centralized log aggregation tool, e.g., Kibana. Filtering for that traced in the payment service logs, you might find specific errors, warnings, or SQL queries that took too long, confirming the database as the bottleneck for that particular transaction. This combination allows for rapid identification of the root cause, transforming a complex, needles-in-a-haystack problem into a clear, actionable diagnosis. Conclusion: operability is not an afterthought in microservices. It's a fundamental design consideration. By strategically implementing centralized logging, comprehensive monitoring, and distributed tracing, you equip your teams with the visibility needed to understand, maintain, and rapidly respond to issues in your complex distributed applications. These capabilities are essential for enabling the continuous delivery and high availability that microservices promise. However, as systems become more open and interconnected, security also becomes a paramount concern, which we will address in the next chapter. Chapter 10. Ensuring security in a microservices ecosystem. In a monolithic application, security often involves safeguarding a single perimeter. Access control, authentication, and data protection mechanisms are applied at a few well-defined points. With microservices, this perimeter dissolves. Instead of a single fortress, you have a sprawling village of independent houses, each with its own doors and windows and frequent movement between them. This distributed nature significantly expands the threat surface, making security a more intricate and challenging endeavor. This chapter explores the principles and patterns required to build a secure microservices ecosystem, focusing on how authentication, authorization, communication, and data are protected in a world without a single, easily defendable boundary. Threat surface expansion, the new realities. Consider how microservices expand the attack vectors. More network endpoints. Each microservice typically exposes an API endpoint, increasing the number of potential targets for attacks. More communication paths. Every interservice call is a potential point of interception or compromise. Decentralized deployments. Different teams might use different frameworks or libraries, leading to inconsistencies in security practices or patch levels. Increased complexity. The sheer number of components and their interactions can make security auditing and vulnerability management more difficult. To counter this, security in microservices must shift from a perimeter-based approach to an intrinsic, layered security culture, often referred to as security by design. Principles of secure microservices. Defense in depth. Implement multiple layers of security controls so that if one layer fails, others can still protect the system. This includes network security, application security, data security, and operational security. Least privilege. Grant only the minimum necessary permissions to users, services, and processes required to perform their intended function. This limits the damage if a component is compromised. Zero trust. Never implicitly trust anything inside or outside your network perimeter. Always authenticate and authorize every user and every device service attempting to access a resource. This means trust but verify, shifts to never trust, always verify. Security by design. Build security into your microservices from the ground up, rather than trying to bolt it on as an afterthought. This includes threat modeling, secure coding practices, and automated security testing throughout the development lifecycle. Auditability. Ensure all security-relevant events, logins, access attempts, data modifications are logged and auditable. Authentication and authorization in a distributed context. Central to microservices security is determining who or what is making a request and what they are allowed to do. User authentication, external clients. External users, web browsers, mobile apps typically authenticate at a central identity provider, IDP. This can be your own identity service or a cloud-based solution. Best practices involve OAuth 2.0, a widely used authorization framework that enables third-party applications to obtain limited access to a user's account on an HTTP service. OpenID Connect, OIDC, an identity layer on top of OAuth 2.0, providing single sign-on SSO capabilities and verifying user identity. JSON Web Tokens, JWTs. After successful authentication, the IDP often issues a JWT to the client. This token contains claims about the user, e.g., user ID, roles. JWTs are stateless, meaning services can validate them without needing to call the IDP for every request. The token is then passed with every subsequent request to your microservices. Service-to-service authentication, internal communication. Once an external request is authenticated at the edge, e.g., API gateway, how do internal microservices trust each other? Propagating identity. The API gateway, having authenticated the user, should propagate user identity and relevant claims, e.g., roles or scopes, to the downstream microservices. This is often done by passing the original JWT or by extracting relevant claims and passing them in custom HTTP headers. Mutual TLS, MTLS. For highly sensitive internal communication, MTLS provides strong authentication and encryption. Both the client and server present certificates to verify each other's identity before establishing a connection. Service meshes, discussed in Chapter 13, often provide MTLS as a built-in feature. Internal API keys, use with caution. For machine-to-machine communication where MTLS is not yet implemented, pre-shared API keys can be used, but they require careful management and rotation. Authorization. Once a request's identity is verified, authorization determines what that identity is allowed to do. Role-based access control, RBAC. Users or services are assigned roles, e.g., admin, customer, guest, and roles are granted permissions to resources or actions. Attribute-based access control, ABAC. More granular, authorization decisions are based on a set of attributes associated with the user, resource, action, and environment. E.g., only users in the New York region can access New York customer data. Decentralized versus centralized enforcement, externalized authorization. A dedicated authorization service or framework evaluates policies. This promotes consistency and manages policy complexity centrally. Each service calls out to this authorization service. Internal enforcement. Each service enforces its own authorization rules. This gives greater autonomy, but can lead to inconsistency if not managed carefully. A combination is often used. A central policy decision point with local enforcement within each service. Securing communication. All communication, both external and internal, should be encrypted to prevent eavesdropping and tampering. TLS-SSL, the standard for encrypting data in transit. Ensure that all external APIs, API gateways, and ideally, all internal service-to-service communication use HTTPS, TLS, certificates. Network segmentation. Use virtual private clouds, VPCs, subnets, and network policies, e.g., Kubernetes network policies, to restrict what services can talk to each other. Services should only be able to communicate with the services they depend on. Secrets management. Secrets, API keys, database credentials, encryption keys, private certificates are the keys to your kingdom. Hard-coding them or storing them insecurely is a major vulnerability. Centralized secrets management. Use dedicated secrets management solutions. These tools securely store, distribute, and rotate secrets. HashiCorp Vault, a popular open-source tool for managing secrets, providing dynamic secrets generation and strong audit trails. Cloud provider services. AWS Secrets Manager, Azure Key Vault, Google Secret Manager offer integrated solutions. Kubernetes secrets. While Kubernetes has a native secrets object, it stores secrets base 64 encoded, not encrypted at rest by default. For production, integrate with external secret managers for better security. Container security. The use of containers introduces new security considerations. Vulnerability scanning. Regularly scan your container images and their base images for known vulnerabilities. Integrate this into your CI/CD pipeline. Minimal base images. Use minimal, slim base images, e.g., Alpine Linux, to reduce the attack surface. Least privileged non-root users. Do not run containers as the root user. Configure them to run with the lowest necessary privileges. Runtime security. Implement runtime security tools that monitor container behavior for suspicious activities. Image provenance. Ensure you only use images from trusted registries and that their integrity is verified. Logging and auditing for security. Security-related events must be logged thoroughly for auditing, incident response, and forensic analysis. Audit trails. Log all authentication attempts, success failure, authorization decisions, sensitive data access, and administrative actions. Centralized security logging. Route all security logs to a centralized, tamper-proof logging system, as discussed in Chapter 9 for long-term retention and analysis. Security information and event management, SIEM. Integrate logs into a SIEM system to detect patterns of malicious activity and generate alerts. Practical advice. Threat modeling. Before writing a single line of code, conduct a threat modeling exercise for each service and its interactions. Identify potential threats, vulnerabilities, and countermeasures. Automated security testing. Integrate security tools into your CI/CD pipeline. Static code analysis, SAST, dynamic application security testing, DAST, dependency vulnerability scanning. Regular patching. Keep all components, operating systems, libraries, frameworks, and tools up to date to address known vulnerabilities. Security champions. Designate security champions within development teams who can act as local experts and promote secure coding practices. Incident response plan. Have a clear, well-tested plan for responding to security incidents. Anecdote. The overly permissive internal API. A fast-growing fintech company embraced microservices, allowing teams significant autonomy. One team quickly built a user data service that exposed a rich API for retrieving extensive customer information, including personal identifiable information, PII, and financial details. For convenience, during development, they secured it with a simple internal API key, which was then widely distributed among other internal services that needed minimal access, e.g., notification service that only needed a customer's email. A few months later, a less critical marketing analytics service had a minor security vulnerability. An attacker exploited it to gain access to the service's internal environment. Because the Marketing Analytics Service had access to the broadly shared API key for user data service, the attacker was able to then make unauthorized requests to user data service, downloading millions of customer records. The critical lesson here was the violation of the least privilege principle. The Marketing Analytics Service only needed access to anonymous, aggregated data, or perhaps just customer email addresses for a specific campaign. It certainly did not need credentials that granted full access to PII and financial data. If user data service had enforced granular authorization, e.g., requiring specific OAuth scopes or MTLS with service-specific roles, or if the API key had narrowly defined permissions, the damage would have been contained. The broad internal API key was a single point of failure that led to a massive data breach. Conclusion: securing a microservices architecture is a continuous journey, not a destination. It requires a fundamental shift in mindset from perimeter defense to a more distributed, layered approach, intertwined with every stage of the development lifecycle. By adopting principles like defense in depth and zero trust, implementing robust authentication and authorization mechanisms, encrypting all communication, and practicing diligent secrets and container security, organizations can build highly secure, resilient microservices ecosystems. However, even with the best security, services will inevitably encounter unexpected data or behavior, requiring robust testing strategies for these distributed systems. Our next focus. Chapter 11. Testing distributed systems, challenges and solutions. Building and deploying microservices successfully hinges on effective testing. In a monolithic application, testing strategies often revolve around a single codebase. Unit tests for small components, integration tests for modules, and end-to-end tests for the entire application. However, when you decompose your system into many independent, loosely coupled services, traditional testing approaches quickly become inadequate, difficult to manage, and slow. This chapter explores the unique challenges of testing distributed systems and outlines modern strategies and patterns, emphasizing approaches that enable independent development and deployment velocity while maintaining high quality and reliability. The testing pyramid, revisited for microservices. The traditional testing pyramid suggests a large base of fast, inexpensive unit tests, a mid-layer of integration tests, and a small apex of slow, expensive end-to-end E2E tests. For microservices, this pyramid needs adjustment. Expanded base, unit and component tests become even more critical. Shifted middle, the nature of integration tests changes significantly. Full, cross-service integration tests are less practical. Shrunken apex. End-to-end tests are still necessary, but should be used sparingly due to their inherent flakiness, slowness, and complexity in a distributed environment. The goal is to provide fast, reliable feedback to developers, allowing teams to iterate quickly and deploy independently. Types of tests in a microservices environment. Let's break down the common types of tests and their specific application in microservices. 1. Unit tests. Purpose: to verify the smallest testable parts of a service, functions, methods, classes in isolation. Focus: testing internal logic, algorithms, and data transformations within a single code unit. Execution: fast, automated, run frequently, often on every code change. Microservices relevance remains foundational. Each microservice should have comprehensive unit test coverage. These tests do not involve external dependencies, databases, other services. 2. Component tests, service in isolation. Purpose: to verify the behavior of a single microservice, treating it as a black box, but without involving live external services. Focus: testing the public API of a service, its internal logic, and its interactions with its own local dependencies, e.g., its dedicated database configuration. External service calls are typically mocked or stubbed. Execution: automated, typically run as part of the CI pipeline after unit tests. Microservices relevance, crucial for validating that a service works correctly on its own. This is where you test database schema interactions, business logic execution through the API, and ensuring the service starts up and operates correctly. 3. Integration tests focus on contracts. This is where microservices testing diverges significantly from monoliths. Full integration tests that spin up multiple real services are generally discouraged due to complexity and slowness. Instead, the focus shifts to contract testing. Consumer-driven contract (CDC) testing, purpose, to ensure that a service, the provider, meets the expectations, the contract, of the services that consume its API, the consumers. Mechanism, consumers define their expectations of a provider's API. These expectations are recorded as contracts. Providers then verify that they fulfill these contracts using automated tests. If a provider's change breaks a contract, the test fails, preventing the deployment of a breaking change. Advantages: enables independent deployment. Services can evolve independently as long as they honor their contracts, eliminating the need for full integration tests. Fast feedback: contract tests are typically fast, local, and run as part of the provider's CI pipeline. Clear responsibility: it's explicit who is responsible for a breaking change. Tools: packed Spring Cloud contract. Example: order service consumer expects inventory service provider to have a reserve endpoint that accepts a producted quantity and returns success. True false. Order service defines this contract. Inventory service then runs a test to ensure its reserve endpoint adheres to this exact contract. 4 end-to-end E2E tests. Purpose: to verify an entire business flow or user journey across multiple services, often through the entire system, from the UI to the backend. Execution: slow, complex, prone to flakiness. They require all necessary services to be running and correctly configured in a test environment. Microservices relevance: while still necessary, they should be used very sparingly. Their primary role is to validate the critical user paths and ensure the overall system integration works. Because they are slow and unreliable, too many E2E tests will significantly hamper development velocity. Challenges: environment setup. Spinning up and tearing down environments with dozens of microservices, mock external dependencies, and test data is challenging. Flakiness: network latency, transient failures, and race conditions can lead to inconsistent test results. Debugging: pinpointing the exact service or interaction that caused a failure is difficult. Other important test types: performance tests, load testing, stress testing, and scalability testing to ensure services can handle expected and peak traffic loads and to identify bottlenecks. Resilience tests, chaos engineering, as introduced in Chapter 9, and fault injection. Deliberately introduce failures, e.g., network latency, service outages, to test the system's ability to maintain availability and recover gracefully. Security tests, vulnerability scanning, penetration testing, static dynamic application security testing, SAST/DAST, to ensure the system is protected against common attack vectors. Usability/user acceptance tests, UAT, involving business stakeholders to ensure the system meets their requirements. Test environment management. Managing test environments for microservices is a significant challenge. Key approaches include containerized environments, using Docker Compose or Kubernetes to spin up lightweight, isolated environments for testing. This allows each developer or CI pipeline to have its own dedicated test environment. Virtualization cloud environments, leveraging cloud providers to rapidly provision and deprovision test environments as needed. Test data management, creating and resetting consistent, realistic test data for multiple services is crucial. Techniques include database seeding, specialized test data generation tools, and ephemeral databases for each test run. Anecdote: the case of Megacorp's E2E Hell. Megacorp, a large financial institution, decided to embrace microservices. Teams were empowered to develop and deploy independently. However, they retained their monolithic era testing strategy. Every feature change, no matter how small, required passing a suite of 2,000 end-to-end regression tests before release. It was purgatory, recounts David, a former lead developer at Megacorp. Our 2,000 E2E tests took 6 hours to run, assuming nothing broke. They were notoriously flaky. A network hiccup on a Saturday morning could trigger a red build, and then you'd spend Monday trying to reproduce it or just rerun it until it passed. The critical path for any new feature involved hours of waiting for the eTOE suite. Teams, desperate to get their features out, would often get into merge-train conflicts, blocking each other's releases. They had gained the ability to independently develop, but lost the power to independently deploy. The eTOE suite, once a safety net, became a lead balloon strapping them down. It wasn't until they adopted consumer-driven contract testing and significantly reduced their eTOE suite to only the very highest-level business flows that they truly unlocked the promise of microservices. CDC tests provided the confidence that APIs wouldn't break, while the few eTOE tests confirmed overall system integration. The investment in robust unit and component tests significantly reduced the need for the costly top of the pyramid. Conclusion: testing a microservices architecture requires a shift in mindset and tooling. Moving away from heavy, monolithic end-to-end tests towards a greater emphasis on fast, automated unit, component, and especially consumer-driven contract tests provides the necessary confidence and agility. While the challenges of distributed testing are real, adopting these modern strategies empowers teams to deliver high-quality software rapidly and reliably. With a solid testing foundation, you're ready to explore the vast array of microservices design patterns, which provide solutions to common challenges, an area we'll delve into next. Chapter 12: Mastering Microservices Design Patterns. As we've explored the complexities of building and operating microservices, a recurring theme emerges. Many challenges are common across different applications and organizations. Fortunately, experienced architects and developers have encountered these challenges before and devised widely accepted solutions, known as design patterns. Microservices design patterns are reusable solutions to common problems that arise when building distributed systems. They are not off-the-shelf components, but rather conceptual blueprints that guide your design decisions, providing a shared vocabulary and proven approaches. Understanding and applying these patterns effectively is key to building resilient, scalable, and maintainable microservices architectures. This chapter categorizes and elaborates on some of the most critical microservices design patterns, providing practical context for their application. Service decomposition patterns. These patterns guide how you break down your application into individual services. We briefly touched upon the foundational concept of bounded context in Chapter 5. Decomposition by business capability. Description. This is the primary and most recommended approach. Services are designed around specific business capabilities rather than technical layers. Each service encapsulates all the code and data necessary to fulfill a particular business function. Example: in an e-commerce system, instead of user service, product service, order service, you might have customer service, catalog service, order fulfillment service, payment processing service. Each of these represents a distinct part of the business domain. Benefits: aligns with Conway's law, fosters autonomous teams, promotes high cohesion and loose coupling. When to use: strongly recommended for defining core microservice boundaries. Decomposition by subdomain, DDD influenced. Description: a more granular approach within the business capability, directly influenced by domain-driven designs, concept of bounded contexts. A business capability might contain several subdomains, each with its own context. Example: order fulfillment might be a business capability, but it could be further decomposed into subdomains like order entry, inventory management, and shipping. Each could become a separate service. Benefits: provides finer-grained services, allows deeper domain modeling. When to use: when a business capability is still too complex or encompasses distinct subareas with different ubiquitous languages. Strangler fig pattern. Description: named after a vine that grows around a tree, eventually strangling it. This pattern describes an incremental approach to refactoring a monolithic application into microservices. New functionality or refactored parts of the monolith are built as microservices, and traffic is gradually redirected from the monolith to the new services. Mechanism: an anti-corruption layer often acts as a facade between the old monolith and the new services, translating requests and responses until the old functionality can be fully retired. Example: a monolithic e-commerce site where product search is slow. A new search service is built, and the monolithic UI is gradually updated to call the search service instead of the monolith's internal search function. Benefits: reduces risk compared to a big bang rewrite, allows for continuous delivery, provides immediate value from new services. When to use: the preferred strategy for migrating existing monolithic applications to microservices. Communication patterns: these patterns address how services interact with each other. We covered synchronous and asynchronous communication in Chapter 6. API Gateway. Description: a single entry point for all client requests, routing them to the appropriate microservices. It can also handle request aggregation, authentication, authorization, rate limiting, and protocol translation. Benefits: decouples clients from the internal microservices architecture, provides a centralized point for cross-cutting concerns, simplifies client code. When to use: almost always recommended for external clients, web mobile, interacting with a microservices system. Caveats: can become an anti-pattern, a monolithic gateway, if too much business logic is placed within it. Aggregator. Description: a specific pattern often implemented within an API gateway or a dedicated service, where a single request from a client requires data from multiple backend microservices. The aggregator service collects data from these services and combines it into a single response. Example: a product page might need product details from catalog service, reviews from review service, and pricing from pricing service. An aggregator service handles these calls and composes the final response. Benefits: reduces client-side complexity and chatty network calls. When to use: when rich UI needs to display aggregated data from various sources. Client-side discovery versus server-side discovery. Description: patterns for how client services find the network locations of other services. Client-side, e.g., Netflix Eureka. Client queries a service registry to find instances, then load balances. Server-side, e.g., Kubernetes services, load balancer proxy queries registry and forwards request. Benefits: enables dynamic scaling and failure recovery. When to use: essential for any dynamic microservices environment. Kubernetes typically handles server-side discovery automatically. Resilience patterns. These patterns focus on making microservices robust and capable of handling failures within a distributed environment. Circuit breaker. Description: prevents an application from repeatedly trying to access a service that is down or experiencing failures. Like an electrical circuit breaker, it trips open when a predefined number of failures occur, diverting calls from the failing service. After a timeout, it allows a single test call to see if the service has recovered before fully closing. Benefits: prevents cascading failures, allows the failing service to recover without being hammered by continuous requests, improves fault tolerance. Example: if order service keeps failing to connect to payment service, a circuit breaker would prevent further calls to payment service for a period, allowing order service to immediately return an error or use a fallback mechanism. Tools: Hystrix legacy but concept still valid, Resilience 4J poly. Bulkhead. Description: isolates resources, like threads, connection pools, for different services or components, preventing a failure in one from consuming all available resources and bringing down the entire application. It's like the watertight compartments in a ship. Benefits: limits the blast radius of failures, enhances fault isolation. Example: isolate thread pools that handle calls to payment service from those calling recommendation service. If payment service is slow, only its thread pool gets exhausted, not the entire application's. Retry. Description: automatically reattempts an operation that has failed. It's often combined with an exponential backoff strategy, waiting longer between retries, to avoid overwhelming a recovering service. Benefits: helps overcome transient network issues or temporary service unavailability. When to use: for idempotent operations, operations that produce the same result regardless of how many times they are executed. Not suitable for non-idempotent operations without careful design. Timeout. Description: sets a maximum duration for an operation or a call to an external service. If the operation doesn't complete within the timeout, it's aborted. Benefits: prevents indefinite waiting for unresponsive services, essential for maintaining system responsiveness. Caveats: requires careful tuning. Too short can lead to premature failures, too long can lead to cascading timeouts. Fallback. Description: provides an alternative action or response when a primary service or operation fails. Benefits: allows for graceful degradation of functionality rather than complete failure. Example: if the recommendation service is unavailable, revert to a default list of popular products instead of displaying an error. Data management patterns. These patterns address the complexities of managing data across independent services, especially when distributed transactions are involved. Database per service. Description: each microservice owns its own dedicated database, preventing direct access from other services. All data access is through the service's API. Benefits: critical for service autonomy, allows polyglot persistence, improves fault isolation. When to use: a fundamental principle for microservices. Saga pattern, orchestration versus choreography. Description: for distributed transactions that span multiple services, a saga is a sequence of local transactions, where each transaction updates data within a single service and publishes an event that triggers the next local transaction. Compensation actions are defined to roll back the saga if any step fails. Orchestration-based saga. A central orchestrator service coordinates the sequence of local transactions. Choreography-based saga. Each service reacts to events from other services without a central coordinator. Benefits: ensures eventual consistency across services without using complex distributed transactions, like 2PC. When to use: whenever a business process requires updating data across multiple independent services. CQRS, command query responsibility segregation. Description: separates the model for updating data commands from the model for reading data queries. This means using different data models and potentially different databases for read and write operations. Benefits: scalability. Read and write models can be scaled independently. Optimization. Each model can be optimized for its specific purpose, e.g., highly normalized write model, denormalized read model. Flexibility. Different consistency requirements for reads versus writes. When to use: for complex domains with specific read-side performance or flexibility requirements, or when the read model significantly differs from the write model. Event sourcing. Description: instead of storing the current state of an application, you store a sequence of immutable events that led to that state. The current state is then derived by replaying these events. Benefits: provides a complete audit trail, enables powerful temporal queries, supports strong consistency within an aggregate, naturally integrates with event-driven architectures. When to use: for domains where every state change is important, historical data analysis is critical, or when complex projections of state are needed. Can be used in conjunction with CQRS. Observability patterns. These patterns ensure that your distributed system remains transparent and debuggable. Distributed tracing. Description: assigns a unique ID to a request as it enters the system and propagates this ID through all services it touches. This allows for reconstructing the end-to-end flow of a request. Benefits: crucial for debugging performance issues and understanding request flows in a distributed system. Tools: Jaeger, Zipkin, OpenTelemetry. Health Check API. Description: services expose a simple HTTP endpoint, e.g., health, status, that external monitoring systems can query to determine if the service is operational and ready to serve requests. Benefits: enables load balancers and orchestrators, like Kubernetes, to automatically remove unhealthy instances from rotation and replace them. Log aggregation. Description: collects logs from all microservice instances and centralizes them into a single, searchable store. Benefits: essential for diagnosing issues and security auditing across a distributed system. Tools: ElkStack, Elasticsearch, Logstash, Kibana, Splunk. Practical application: an online restaurant ordering system. Let's imagine an online restaurant ordering system applying a combination of these patterns. Decomposition. Restaurant service, menu service, order service, payment service, kitchen service, delivery service by business capability. API Gateway handles all external requests from customer mobile apps and the restaurant's order management console. It routes requests, authenticates users, and perhaps aggregates menu details. Resilience within order service. When order service calls payment service, it uses a circuit breaker to prevent retrying a failing payment gateway and a timeout to not wait indefinitely. It might use a fallback to allow cash payment if the online payment gateway is temporarily unavailable. Data management, database per service. Each service has its own database. Menu service might use a document database. Payment service uses a relational database. Saga, orchestration-based. An order service orchestrates the order processing saga. Order service creates pending order. Calls payment service to process payment. If payment successful, calls kitchen service to start preparation. If prep started, calls delivery service to assign a driver. If any step fails, order service triggers compensating actions. Observability. Every order request has a distributed trace ID that travels through API Gateway, order service, payment service, kitchen service, delivery service, allowing end-to-end monitoring. All services send JSON-formatted logs to a log aggregation system. All services expose health check APIs for monitoring. Mastering these patterns provides you with a powerful toolkit to tackle the inherent complexities of microservices gracefully. They represent accumulated wisdom, helping to avoid common pitfalls and build more robust and maintainable distributed applications. In the next chapter, we'll delve into more advanced patterns, including the increasingly popular service mesh paradigm and other cross-cutting concerns. Chapter 13: Advanced Patterns and Cross-Cutting Concerns. As microservices architectures mature and the number of services grows, new complexities emerge. While the foundational principles and common patterns discussed in previous chapters provide a strong basis, there are more advanced scenarios and recurring architectural challenges, often called cross-cutting concerns, that require dedicated solutions. This chapter explores some of these advanced patterns, including the increasingly vital service mesh, and delves deeper into how to manage issues that span across multiple services. Asynchronous messaging patterns, revisited. While we introduced message queues and PubSub in Chapter 6, here we consider more specific patterns for their usage beyond simple decoupling. Message broker, description. A central component, like Apache Kafka, RabbitMQ, or AWS SQS SNS, that facilitates communication between services. Publishers send messages to the broker, and subscribers consume them. Purpose. Provides robust decoupling, buffering for peak loads, and reliable delivery guarantees. It acts as an intermediary, removing direct dependencies between sender and receiver. Benefits. High scalability, resilience, and flexibility in communication. When to use. For event-driven architectures, long-running processes, or when highly decoupled, publish-subscribe communication is required. Request response over messaging. Description. While messaging is inherently asynchronous, sometimes a service needs an immediate response after sending a message. This pattern involves the sender publishing a message with a correlation ID and a reply to address, e.g., a temporary queue, and then actively listening for a response from the recipient on that reply to address, identified by the correlation ID. Purpose. Provides a synchronous-like interaction over an asynchronous backbone, useful when a service needs to wait for a result, but still wants the benefits of a message broker for reliability and decoupling. Benefits. Combines the reliability of messaging with the interactivity of request response. Caveats. Adds complexity, requires careful handling of timeouts and retries, still susceptible to the challenges of distributed transactions if not managed with sagas. Serverless and function as a service, FaaS. The rise of serverless computing, particularly function as a service, FaaS, offers an interesting dimension to microservices. What it is. FaaS platforms, e.g., AWS Lambda, Azure Functions, Google Cloud Functions, allow developers to deploy and run small, single-purpose functions without provisioning or managing servers. The cloud provider handles scaling, patching, and operational overhead. Microservices and serverless, are they the same? Not exactly. Serverless functions are often referred to as nanoservices due to their extremely small, single-purpose nature. While microservices are often deployed to serverless platforms, a microservice can be larger and encompass more business logic than a typical FAS function. When to use FAS for microservices, event-driven workloads, functions are ideal for reacting to specific events, e.g., image upload, database change, message queue event. Highly sporadic workloads. Pay-per-execution model makes it cost-effective for functions that are invoked infrequently. Stateless operations. FAS functions are typically stateless, making them easy to scale horizontally. Non-performance critical. While performant, FAS functions can have cold start issues, which make them less suitable for extremely low latency, high-throughput synchronous APIs directly exposed to end users unless specialized warm-up strategies are employed. FAS complements microservices by providing an even finer-grained decomposition for specific event handlers or utility functions, offloading more operational burden to the cloud provider. The service mesh. As your microservices landscape expands, managing all the cross-cutting concerns, like traffic management, security, and observability, across potentially hundreds of services becomes overwhelming. This is where a service mesh comes in. What it is: a dedicated infrastructure layer that handles service-to-service communication within your application. It operates by deploying a proxy, called a sidecar proxy, alongside each microservice instance. All network traffic to and from the microservice flows through this sidecar proxy. The collection of these proxies, along with a control plane to manage them, forms the service mesh. Key features handled by the sidecar proxy, configured by the control plane: traffic management, routing, e.g., A/B testing, canary releases, load balancing, traffic splitting, retry logic. Resilience automatically implements patterns like circuit breakers, timeouts, retries, and rate limiting at the network level. Security handles mutual TLS, MTLS for all service-to-service communication, identity verification, and fine-grained access control policies. Observability automatically collects metrics, traces, and logs for all inter-service communication, centralizing data collection. Policy enforcement enforces access policies and quotas. Tools: Istio, Linkerd, Console Connect. Benefits: offloads developers. Developers don't need to implement these cross-cutting concerns in their application code, allowing them to focus on business logic. Centralized control. Operations teams can manage and enforce network policies, security, and traffic patterns from a single control plane. Consistent implementation ensures that resilience and security features are applied uniformly across all services, regardless of the language or framework used. Drawbacks: increased complexity, introduces a new layer of infrastructure to manage and understand. Resource overhead: each sidecar proxy consumes resources, CPU, memory. Latency adds a small amount of latency due to the additional hop through the proxy. Learning curve requires significant operational expertise. When to use a service mesh. For large-scale microservices deployments, dozens to hundreds of services, where managing cross-cutting concerns manually becomes prohibitive, or where robust security and traffic control features are critical. For smaller applications, it might be an unnecessary overhead. Other cross-cutting concerns. Beyond what a service mesh might handle, several other concerns span across multiple services and require a consistent approach. Configuration management. Description: externalizing application configuration, e.g., database connection strings, API keys, feature flags from application code. Services retrieve their configuration at startup or runtime. Tools: config map/secret, Kubernetes, HashiCorp console, Spring Cloud config, environment variables. Benefits: allows changing behavior without redeploying code, promotes consistency across environments, enables secure management of secrets. Feature toggles/feature flags. Description: a technique that allows you to turn specific features on or off during runtime without deploying new code. The feature logic is present in the code, but is activated or deactivated based on a configuration flag. Benefits: decouples deployment from release, enables A/B testing, allows dark launches, deploying features to production but keeping them hidden, easy rollback of a faulty feature without a full service rollback. Tools: launch darkly, optimizely, or homegrown solutions. Rate limiting. Description: controlling the rate at which an API endpoint or service can be invoked, typically to prevent abuse, protect against DOS attacks, or manage resource consumption. Implementation: often applied at the API gateway or within the service mesh, but can also be implemented within individual services. Benefits: improves stability and prevents services from being overwhelmed. Auditing. Description: recording actions performed by users and services for compliance, security, and troubleshooting purposes. This often involves logging specific events in a structured, immutable way. Benefits: provides accountability, crucial for incident response and regulatory compliance. Batch processing in microservices. While many microservices focus on real-time, online processing, sometimes you need to handle large volumes of data offline. Pattern: instead of building large monolithic batch jobs, decompose them into smaller, independent microservices or functions triggered by events. Mechanism: use message queues, e.g. Kafka, to queue up tasks. FAS can be excellent for small, event-triggered batch processing tasks. Specialized batch processors, e.g. Apache Spark jobs, AWS Batch, can be integrated as independent components. Benefits: scalability, fault tolerance, and independent deployment of batch components. Practical considerations: when to adopt advanced patterns. Introducing advanced patterns like a service mesh adds significant operational complexity and resource overhead. It's crucial to adopt them incrementally, only when the benefits clearly outweigh the costs. Start simple. Begin with foundational microservices, REST APIs, and basic CI/CD. Address observable pain points. Introduce a service mesh when you struggle with consistent security policies, traffic management, or comprehensive observability across dozens of services. Measure benefits. Use metrics MTTR, deployment frequency, error rates to justify the investment in these advanced tools. Debate: the fat client versus thin client in a distributed UI. With microservices, a debate often arises around the user interface. Thin client, traditional MVC SPA. A single, monolithic front-end application, e.g., a single-page application or a mobile app, talks to the API gateway, which then fans out requests to various microservices. The front-end holds all UI logic. Pros: simpler front-end architecture, easier for a single front-end team. Cons: front-end can become a bottleneck for feature development, might require back-end changes for simple UI tweaks if aggregates are needed. Fat client/micro frontends. The front-end itself is broken down into smaller, independent components, micro frontends, each owned by a specific microservice team or a dedicated front-end team collaborating closely. Pros: aligns with Conway's Law, teams own features end-to-end, faster independent UI development, technology flexibility for front-end. Cons: more complex front-end architecture, integration challenges, how to compose micro front-ends, increased operational overhead for front-end deployments. The choice depends on team structure, application complexity, and desired development velocity. For large, complex applications with many independent features, micro frontends can extend the benefits of microservices to the UI layer. Conclusion: as your microservices landscape expands, managing the interconnectedness and common needs of your applications becomes more critical. Advanced patterns like service mesh, combined with robust solutions for configuration, feature management, and auditing, provide powerful mechanisms to scale your architecture while offloading complexity from individual services. They enable teams to focus on core business logic, further enhancing agility and innovation. However, the path to microservices is rarely a greenfield project. Most organizations begin with a legacy system and face the challenge of migrating existing assets. This strategic migration, along with the profound organizational shifts it entails, is the subject of our next chapter. Chapter 14, Strategic Migration and Organizational Impact. The journey to microservices is rarely a greenfield endeavor where you start from scratch. For most organizations, it involves migrating an existing, often deeply entrenched, monolithic application. This transition is not a mere technical uplift. It represents a significant strategic shift that impacts not only your technology stack, but, perhaps even more profoundly, your organizational structure, culture, and processes. Ignoring the human and organizational aspects of this transformation is a common pitfall that can derail even the most technically sound microservices initiative. This chapter explores proven strategies for migrating from monoliths and delves into the critical organizational changes required to harness the full potential of a microservices architecture. Migration strategies for existing monoliths. Rewriting an entire monolithic application from scratch as microservices, the Big Bang rewrite, is almost universally discouraged. It's incredibly risky, expensive, and often results in failure. Instead, incremental, lower-risk approaches are preferred. One, the strangler fig pattern, detailed. This pattern, introduced briefly in Chapter 12 and coined by Martin Fowler, is the most recommended and widely adopted approach for migrating from a monolith. It involves gradually replacing functionality in the monolith with new microservices, piece by piece, until the monolith eventually strangles itself and can be retired. Mechanism: identify seams. Find logical boundaries or modules within the monolith that can be extracted as independent services. These often align with bounded contexts. Chapter 5. Build new service. Develop the new microservice for the identified functionality. This service is built using microservices principles, potentially with a new technology stack and its own database. Redirect traffic. Implement a routing layer, often using an API gateway, reverse proxy, or service mesh, to gradually redirect traffic for the extracted functionality from the monolith to the new service. Anti-corruption layer, ACL. Often, the new microservice needs to interact with the remaining monolith. An ACL, Chapter 5, acts as a translation layer, preventing the new, clean domain model from being corrupted by the legacy model of the monolith. It translates requests and data formats between the old and new systems. Deprecate old code. Once all traffic is successfully routed to the new microservice, the corresponding code in the monolith can be removed or disabled. Continue this process, iteratively extracting functionality until the monolith shrinks down to nothing or to a very small, manageable core. Benefits: reduced risk, no single traumatic cutover. Functionality can be moved in small, manageable steps. Continuous value delivery. New services can be deployed and deliver value immediately. Learning opportunity. Teams gain experience with microservices technology and practices incrementally. No frozen time. Business development can continue while the migration happens. Challenges and best practices. Data migration. Extracting data from the monolith's database to the new services database can be complex. Strategies like dual write, writing to both databases during transition, or snapshotting replication are common. Transactionality. Ensuring consistency for processes that span the new service and the remaining monolith, e.g., using sagas. Coordination. Requires careful planning and communication between teams working on new services and those maintaining the monolith. Monitoring. Essential to detect issues quickly when redirecting traffic. 2. Branch by abstraction. Description. This technique involves creating an abstraction layer around a logical component within the monolith that you intend to extract. All internal calls to that component are routed through this new abstraction. Once the abstraction is complete, you can then replace the implementation of the abstraction with the new microservice. Benefits. Provides a cleaner break than direct extraction if complex internal dependencies exist. When to use: when the functionality to be extracted is deeply embedded with many internal callers. 3. Big Bang rewrite. Avoid this. Description. Stopping all development on the existing monolith and starting from scratch to rewrite the entire application as a microservices architecture. Risks: high failure rate. many famous cases of projects failing to deliver anything after years of effort. Business stagnation. No new features or bug fixes delivered on the old system, while the new one takes years. Over budget, over time. Scope creep and unforeseen complexities are common. Loss of knowledge. Developers might leave, taking critical domain knowledge with them. Demoralization. Long, arduous projects without visible progress can lead to team burnout. When to use? Almost never. The only extremely rare exceptions might be if the existing system is completely unmaintainable, has zero business value, or poses unacceptable security risks, and the new system is very small and simple. Organizational transformation. Technical changes alone are insufficient for a successful microservices adoption. The most profound and often most challenging aspects of the transition are organizational and cultural. 1. Conway's Law Revisited. Aligning teams with business capabilities. As discussed in Chapter 4, Conway's Law states that your system's architecture will mirror your organization's communication structure. For microservices, this means, from component teams to product teams, move away from teams organized around technical layers, e.g., database team, front-end team, QA team, or generic components. Autonomous teams. Form small, cross-functional teams, typically 5 to 10 people, that own one or a few microservices end-to-end. These teams are responsible for the entire lifecycle of their services: design, development, testing, deployment, and operation, on-call. Business capability alignment. Each team should be aligned with a specific business capability or bounded context, e.g., order fulfillment team, customer accounts team. This fosters domain expertise and full ownership. 2. The DevOps culture. Breaking down silos. Microservices thrive in a DevOps culture, which emphasizes collaboration, communication, and integration between development and operations teams. With each team owning its services from build to run, the traditional handover between dev and ops vanishes. You build it, you run it. Developers are responsible for the operational aspects of their code. This increases empathy for operational challenges and incentivizes building high-quality, observable, and resilient services. Automation. DevOps relies heavily on automation, CI/CD, infrastructure as code, to enable rapid and reliable deployments. Shared responsibility. Quality, security, and performance are shared responsibilities across the entire team and value stream. 3. Communication challenges. Managing coordination. While microservices reduce coordination between development teams at runtime, they introduce a new set of communication and coordination challenges at an organizational level. Service contracts. Teams must rigorously define and adhere to their service APIs and communication contracts, Chapter 6 and 11. Shared understanding. Maintaining a high-level understanding of the entire microservices ecosystem among all teams. Community of practice. Fostering a community of practice, or guild, where developers can share knowledge, best practices, and collaborate on shared tools or architectural guidelines, e.g., common logging libraries, security standards. This balance between autonomy and consistency is key. Governance. Moving from prescriptive architecture review boards to more advisory architecture enablement teams that provide guidance, patterns, and tooling rather than rigid rules. 4. Skill gaps. Reskilling your workforce. The transition requires new skills for both developers and operations staff. Distributed systems thinking. Developers need to understand eventual consistency, failure modes, observability, and network programming. Containerization and orchestration. Familiarity with Docker, Kubernetes, and cloud-native practices. DevOps tools and practices. Expertise in CI/CD pipelines, automation, and monitoring tools. Troubleshooting. Mastering the tools and techniques for debugging distributed systems, Chapter 9. Organizations must invest heavily in training, internal workshops, and hiring talent with these skills. Leadership and governance. Effective leadership is crucial to navigate the organizational complexities. Empowerment with guardrails. Leaders must empower teams with autonomy to innovate, but also provide clear architectural guardrails, e.g., mandated observability standards, API design guidelines, to ensure consistency and prevent chaos. Executive buy-in. Microservices initiatives often require significant investment and long-term commitment. Strong executive support is essential to drive the transformation. Continuous improvement. Embrace the idea that the architecture will evolve. Regular retrospectives and reviews help adapt the process. Metrics for success. How do you know your microservices adoption is successful? Look beyond just delivering services. Measure the impact on deployment frequency. How often can a team deploy changes to production? Should increase significantly. Lead time for changes. How long does it take for a code change to go from commit to production? Should decrease. Mean time to recovery, MTTR. How long does it take to restore service after a failure? Should decrease due to isolated failures and better observability. Change failure rate. What percentage of deployments result in a service degradation or outage? Should decrease over time due to smaller, less risky deployments. Team productivity and morale. Are teams more productive and satisfied? These metrics, popularized by the DevOps Research and Assessment (DORA) reports, provide a clear indication of organizational performance and the success of your transformation. Case study. Transformco's journey. Transformco, a large insurance provider, faced stagnant innovation due to their monolithic policy management system. New product launches took years, customer experience improvements were slow, and their competitors were gaining ground. They embarked on a microservices journey. Their initial approach was purely technical, extract services but maintain existing team structures. Predictably, this led to frustration. The policy admin team, working on a new policy service, constantly waited on the data migration team for database schemas and on the operations team for deployment. Inspired by Conway's Law, their CTO initiated a radical organizational change. They dissolved the traditional functional teams and formed product delivery units, each responsible for a specific business line like auto insurance, home insurance, or claims processing. Each unit became a fully autonomous, cross-functional team, devs, QA, ops, owning their services end-to-end. It was jarring at first, admitted Maria, head of the auto insurance unit. Developers had to learn about operational metrics, and we all had to get comfortable with owning our services 24/7. But the change in velocity was incredible. We went from quarterly releases to weekly, and for some services, daily. Our MTTR for incidents dropped by 70%. More importantly, our teams felt truly empowered. They owned their destiny. Transformco also invested heavily in a centralized, platform engineering team that provided shared tooling, Kubernetes templates, CI/CD pipelines, observability dashboards, and architectural guidance, rather than mandating design choices. This allowed teams to build their services efficiently while adhering to common standards. Their multi-year journey was challenging, but through persistent technical and organizational adjustments, Transformco turned their slow-moving behemoth into an agile, innovative powerhouse. Conclusion: migrating to microservices is a holistic transformation. It demands a strategic, incremental approach to technical decomposition, with the strangler fig pattern as your primary tool. More importantly, it necessitates a fundamental shift in organizational structure towards autonomous, cross-functional teams aligned with business capabilities, underpinned by a strong DevOps culture. By combining technical migration with an equally robust organizational change management plan, organizations can unlock unprecedented agility, accelerate innovation, and truly architect a future that is resilient, scalable, and responsive to ever-changing business needs. As we move ahead, the microservices landscape itself continues to evolve, bringing new trends and challenges, which we will touch upon in our final chapter. Chapter 15, The Road Ahead. Emerging Trends and Continuous Evolution. We have journeyed through the intricate landscape of microservices architecture. From its foundational principles and practical implementation, patterns to the critical challenges of data management, security, testing, and organizational transformation. As an architect or developer in this space, one truth resonates above all: the software world never stands still. Microservices, while a powerful and mature architectural style, continue to evolve. New technologies emerge, existing tools gain capabilities, and best practices are continuously refined. This final chapter looks to the horizon, discussing emerging trends, reaffirming the importance of operational excellence, and emphasizing the human element in this dynamic field. Serverless evolution beyond FaaS. While functions as a service, FaaS, was the initial poster child of serverless, the concept is expanding. We're seeing serverless containers. Platforms like AWS Fargate allow you to run traditional containers, and thus microservices, without managing the underlying servers. This bridges the gap between FaaS's operational simplicity and Kubernetes container flexibility. Workflow orchestration. Tools like AWS Step Functions or Azure Logic Apps allow you to define and orchestrate complex business workflows that span multiple FaaS functions, traditional microservices, or even external APIs. This brings structure to asynchronous communication, reducing the callback hell of chained events. Persistent serverless options. Innovations in serverless databases and data stores that handle scaling and operational burden without requiring server provisioning, offering a truly serverless-first stack. This evolution highlights a continuing trend, abstracting away more infrastructure concerns, allowing engineering teams to focus even more on business logic. Edge computing and microservices. As the Internet of Things, IoT, proliferates and latency becomes a critical factor for certain applications, e.g., augmented reality, autonomous vehicles, processing data closer to its source, at the edge becomes vital. Microservices at the edge. Small, highly specialized microservices can be deployed on edge devices or edge data centers to process data locally, reducing reliance on centralized cloud infrastructure. Hybrid architectures. This implies complex hybrid cloud edge architectures where some services reside in the central cloud and others extend to the edge, necessitating robust communication and synchronization strategies. New challenges. Managing, deploying, and observing services across a vast, heterogeneous network of edge devices introduces new operational complexities. WebAssembly, WASM, and microservices. WebAssembly, initially designed for web browsers, is gaining traction as a lightweight, secure, and portable runtime for non-browser environments, including server-side applications. Potential impact. WASM modules are extremely fast to start, have a small memory footprint, and offer strong sandbox security. This makes them potentially ideal candidates for highly efficient, language-agnostic microservices, even smaller than traditional containers, that can run anywhere. Server-side WASM runtimes. Projects like WASI, WebAssembly System Interface, aim to standardize how WASM interacts with system resources on the server, paving the way for its wider adoption in microservices infrastructure. Event-driven architectures, deep dive. While we've discussed event-driven patterns, a deeper adoption of EDA is emerging as a dominant paradigm. Event streaming platforms. Apache Kafka has become central to many modern microservices architectures, acting as a highly scalable, durable, and fault-tolerant backbone for event communication. Stream processing. Building applications that continuously process streams of events, e.g., using Kafka Streams or Flink to derive insights, trigger actions, or create real-time materialized views. Complex event processing, SEP. Identifying patterns and correlations within large volumes of events to detect anomalies or trigger sophisticated business rules. This deeper shift towards EDA means thinking in terms of events, streams, and reactions, rather than just request-response APIs. Data mesh principles. Building on the concept of decentralized data ownership from Chapter 7, the data mesh is an emerging socio-technical paradigm that decentralizes data ownership from a central data team to individual domain-oriented teams. Key principles: domain-oriented ownership. Data is owned and produced by the domain teams who generate it, treating data as a product. Data as a product. Data is made easily discoverable, addressable, trustworthy, and interoperable for other domains to consume. Self-serve data platform. A platform that abstracts away the technical complexities of data infrastructure. Federated computational governance, decentralized decision-making with global policies. Relevance to microservices. directly complements microservices by applying similar principles of autonomy and domain ownership to data assets. It aims to solve the problem of data silos and slow data delivery often experienced in large enterprises. AI, ML, and microservices. The integration of artificial intelligence and machine learning models is increasingly happening within microservices architectures. ML models as services. Training and deploying ML models as independent prediction services, allowing other microservices to consume their intelligence via APIs. ML Ops. The practice of applying DevOps principles to machine learning, focusing on automating the lifecycle of ML models, from experimentation and training to deployment and monitoring in production. Microservices tooling and practices are highly beneficial here. Observability beyond basics, AI Ops. The sheer volume of telemetry data generated by microservices can be overwhelming. AI Ops, artificial intelligence for IT operations, aims to use AI ML to automate and enhance IT operations, particularly in monitoring and incident management. Anomaly detection. AI ML algorithms analyze metrics and logs to automatically detect unusual patterns that might indicate an impending issue, often before thresholds are breached. Root cause analysis. Using AI to correlate events across different services, identify patterns, and suggest potential root causes for complex distributed problems. Predictive monitoring. Predicting future issues based on historical patterns. AI Ops promises to reduce alert fatigue and accelerate incident resolution in complex distributed systems. Operational excellence and sustainability. As microservices become pervasive, the focus on operational excellence deepens. Site reliability engineering, SRE. Teams increasingly adopt SRE principles, treating operations as a software engineering discipline, focusing on service-level objectives, SLOs, and error budgets. Chaos engineering maturity, moving beyond simple fault injection to continuous, automated chaos experiments as part of the production environment. Green software engineering, a growing awareness of the environmental impact of software. Microservices can consume resources more efficiently when designed well, e.g., scaling only what's needed. But the operational overhead of managing many services can also increase energy consumption. This leads to a focus on making microservices deployments more energy efficient and reducing their carbon footprint. The human factor, continuous learning and evolution. Finally, perhaps the most critical trend is the sustained focus on the human factor. The microservices journey is a continuous learning process. Talent development. The industry needs architects and engineers who are not just experts in a single technology, but possess a holistic understanding of distributed systems, cloud-native patterns, and DevOps practices. Team cohesion and avoiding burnout. While autonomy is great, managing the cognitive load and potential for alert fatigue in distributed systems is vital. SRE practices, robust automation, and psychological safety are crucial for preventing burnout. Knowledge sharing, fostering internal communities of practice, writing internal documentation, and promoting cross-team learning are essential for success. The architectural choices we make today will shape our systems for years to come. The goal is not to adopt every new trend, but to understand your specific business needs, team capabilities, and existing context. Concluding challenge to the reader. Microservices architecture is not a static destination. It's a dynamic, evolving landscape. The principles laid out in this book, loose coupling, high cohesion, autonomy, resilience, and observability, are timeless. But how they are implemented, the tools we use, and the patterns we apply will continue to change. Your journey into microservices design, implementation, and patterns is just beginning. Embrace continuous learning, question assumptions, share your knowledge, and contribute to the collective wisdom of the software development community. Build with purpose, operate with visibility, and evolve with agility. The future of software is in your hands. Suggestions for further reading. Building Microservices by Sam Newman, a foundational text covering core concepts. Microservices Patterns by Chris Richardson, an excellent deep dive into design patterns. Domain-driven design, Tackling Complexity in the Heart of Software by Eric Evans, the definitive book on DDD. The Phoenix Project and The Unicorn Project by Gene Kim, fictional narratives that brilliantly illustrate DevOps and architectural principles in practice. Accelerate by Nicole Forsgren, Jez Humble, and Gene Kim, data-driven insights into high-performing organizations and DevOps. Martin Fowler's blog, martinfowler.com, a rich source of articles on microservices, patterns, and software architecture. The Cloud Native Computing Foundation, CNCF Landscape, for exploring the vast ecosystem of cloud-native tools.